Hello? Yes?
We have joined.
Yeah. Yes. We have joined. We have just joined.
What is the time? 58. Where is the question?
I don't think anything is zero.
Okay, you come in. Let me see. You are not being seen.
Good morning, ma'am. So, shall we start now?
Yeah.
Yes.
Okay.
Wait.
So, good morning.
Just a second. You are not being seen properly. Now you sit yourself carefully. Your face is.
Okay, so let's start. Good morning, everyone. I welcome you all to the first talk of today's session. My name is Harita, and I'll be moderating the morning session for today. So, I welcome Professor Hemaindi Sarbadigari for continuing her lecture on cardinal arithmetic. So, handing over to you, ma'am.
Shall I?
Yes. Okay, so we should
start sharing your screen.
Yeah.
Yeah.
Was disabled participant screen sharing?
You have disabled?
Just wait a second, ma'am. Give me a second, ma'am. Yeah, now you can do. Yes, it's visible now.
Okay. Let me make it full screen.
Yeah, sure.
No. Okay.
Yeah, it's full screen now.
No, I want to minimize.
Minimize what?
No.
Okay.
So,
So I go back.
proposition A.
So I'm going back because there's a question from somebody listening on YouTube.
X2.
So there's S2, is it? Oh, so the question is this. Here, for 2x to the power y to the power z, and cardinality of that and cardinality of x to the power y cross z. And the question is, what happens if y is empty? Is there any problem?
And Z is not.
And z is not. Okay, so if y is empty, then x to the power y is 1. It's the empty function. And so this becomes x to the power z. This becomes 1 to the power z, which is 1. And x to the power y cross z. Now, if y is empty, y cross z is also empty. So this also becomes 1. So I think there's no problem. All right. So are there...
Just a second. Agnik, I think you can post something on YouTube and that will be forwarded and displayed here. You cannot talk, but you can post your things from YouTube. That's what organizer told me. And that can be displayed in the chat box here, and we will know whether you agree or not.
Yeah, so we'll convey the messages for you, sir. Whatever the questions are there from YouTube Live, we will convey to you during the lecture.
All right. So now, yesterday, perhaps I went rather fast. So is there anything anybody would like me to go over again? We have time. So any questions about yesterday's or any doubts or problems? Anything, anybody?
Ma'am, I think I had a quick question.
Yes. Yes.
So the question is that if we consider the pairs of rationals in R2,
Yes.
so I think that set would be uncountable.
Pairs of rationals.
Yes, pairs of
Would-
rationals, and if we try to, I mean, let's say
Just a minute. Are rationals countable or uncountable?
rationals are countable, right?
Okay,
Rationals are countable.
so that is like n, right? As far as cardinality is concerned,
Uh,
rationals, I mean.
yes,
Uh,
yes,
okay, so pairs of rationals, that would be like n cross n, no?
yes, yes.
So isn't that
I mean,
countable? Haven't we proved
okay. I mean,
anything?
what I
Yes.
thought was that, let's say I pick up one rational, any one
Uh,
rational,
uh,
and I consider all the other rationals in the
yes.
I mean R. So that's
Wait a minute. Rationals are is all reals, but you are only looking at rationals there. That
yes,
okay.
yes.
All right then. That's still
Uh,
countable, I suppose.
uh,
Right? Set
I
of
mean,
rationals. Uh,
like
just
let's say I
just a
pick up.
minute. Are you convinced that the set of rationals is countable?
Yes, yes, I am.
Okay. Now you are looking at rationals cross rationals. Is that it?
Yes,
Pairs of
yes,
rationals.
yes. Yeah,
So that is like x cross x with x
yeah,
countable.
yes. And
So
that's
that is
why.
not, you are not convinced that that is countable?
Ma'am, what I thought was that let's pick up one rational, any one rational. Let's say that is m,
Yes.
and if we, I'm just trying to do it the brute force way. So if I consider all the other rationals, let's say positive rationals
Uh,
for our convenience,
uh,
then we would get like an unending string, and then I would have some other rational. Let's say for example m plus one. So that would be another unending string. So it kind of is counterintuitive that it is countable.
well,
So
no, I don't get this. Unending is just infinite. Huh? It has
yeah,
nothing to do with, it can still be countable. So I don't
okay,
exactly get this. But look here, if you have a proof that something is countable, you
yeah.
cannot possibly, by some other method, prove it is uncountable, can you? That is not
uh,
possible, right?
Ma'am, can you repeat that?
Huh? What's that?
Can you repeat? Can you repeat what you
Suppose you
just?
have proved a set to be countable, huh?
Yeah, yeah,
Which you seem to have done.
yeah.
Then how can you now go around and try to prove it
Yeah,
is
yeah,
also uncountable?
yeah, yeah.
So,
Fine.
okay. Do you get what I'm saying?
Yes, ma'am. Yeah.
Okay. Okay. All right. Now, anything more? Anybody? Well, somebody had a problem yesterday with, I was defining this partial ordered set, and I had a, wait a minute. I think I know how to help there a bit. So let me see. I wrote a BG here, and then later on a B came in the proof, and I think there was a confusion. Now this BG you can change to C, CK or anything you like. This is just take any element of B here. So somebody had this doubt, so I'm trying to clear it. There's nothing sacred about B here. You could call it C. It's just take any arbitrary element of B, and AF comes before that if something happens. That's all. Okay. Anything else? Anybody? Or anything you would like me to go over? Okay, if not, then just a minute. I think this is as far as I got. So I will do this one theorem about again, still on a similar vein about comparing sizes of cardinality of sets and so on. And then we'll go to cardinal arithmetic. So this says I take two non-empty families of sets indexed by the same I. So xi and yi, I in I, are two non-empty families of sets. And xi's are pairwise disjoint because I'm going to take union, the cardinality. And xi's are smaller than yi, cardinality wise. I mean, each xi is smaller than the corresponding yi. Then cardinality of union xi is actually strictly lesser than cardinality of the product of y. This is okay, finite, infinite, doesn't matter, anything. All right. And now this is a proof, some manipulation. That, okay, so I just proved this straight out. Since now, yi's are of course non-empty now, because xi's are less than yi. So look at the product. Product consists of actually all choice functions picking one element from each yi. Fi is in yi. That. So, and by AC, that is a non-empty set. Oh, now, all right. And since this mod xi is less than mod yi, you get an injection from xi into yi. And this will not be onto. So some point is always left out. So suppose, call this injection fi, and suppose yi is a point outside its range. It is always there. Now, I am defining an injection from union xi to this product of yi's. And then I'll show that you can't have an onto. And that will do it. That will say, you see, injection says that union xi, cardinality of that, is less than equal to the cardinality of product yi's. And then if I can show that this is not an onto map, I mean, there is no onto map, then I'll be done, right? That means there's no bijection. So they cannot be equal. So the strict less than comes. All right, everyone? Okay. So this is how I define the map. From each xi, I am defining an hi. Xi is a disjoint. So put together, that will give you a map from union xi. So, and this hi should go into product of yi's. So I should say what the jth coordinate is for any given j. So hix, the ith coordinate is fix, and x is in xi, remember. So fi was that function going from xi into yi. So ith coordinate is fix, and all other coordinates are corresponding y's outside the range of the f's. You know, this is yj if j is not equal to I, and yj is outside the range of fj. And that makes this 1, 1. All right.
Ma'am, can you please go back? Just,
yes, where? Here.
Just defining this function by AC, I'm trying to follow that.
Defining this function by AC. No, this is a specific definition.
Yeah.
I see. You choose the yi's by AC. That is
okay.
Because what is it? For each I, yi minus fixi is non-empty. The fi is non-empty. So I have this family of non-empty sets for each I, non-empty sets indexed by I. So if I want to choose a point from each, then I use AC. This is a whole family of sets.
No, ma'am.
Yes?
Ma'am, you're using AC to pick the injection also, right?
Oh, where? Just a minute.
Finally, you do because you choose.
Yes. Oh, I see. Okay. Because the yi's are, yes, I choose yi. Okay. No, yi is already chosen.
No, ma'am, I'm saying the injection that you've chosen from xi to yi, right?
Oh, the injection that is chosen from xi to yi. Well, no, for each I. Okay, okay, okay,
Yes.
okay. All right, all right. Since I'm doing it for each I, all right, I agree. I agree. If it was one, then I wouldn't. Since it's a whole family, I agree. Yes, I'm using AC. Yes, that's right. So, all right. Then given that, is it all right that the HI is 1, 1 for each I? And
So,
then, yes?
can you explain how HI is 1, 1? I didn't get that part.
Oh, how is HI 1, 1? Because you take two x's, if they both come from xi, then on the ith coordinate, hix is different because fi is 1, 1. Is that okay?
Yes, ma'am.
Acha. Now, suppose one comes from xi and the other comes, just a minute. What did I say? Oh,
One comes from
X.
XI.
Okay, okay. Suppose one of them comes from xi and the other from some xj, then
Yeah, ma'am. I get it because one is in the set and the other is not in the set,
yes,
right?
yes, yes,
Yeah.
right. Okay. Now we have to show, if you accept this, we have to show that there's no map from union xi onto product y and no map onto it. So if there's no surjection, then the two sets cannot be equal in cardinality. So this union xi must be smaller. Okay. So suppose there's a surjection, we'll get a contradiction. Okay, so now, all right, so there's no, by the way, okay, I should have said this, that if there is a map from x onto y, then cardinality of y is less than equal to cardinality of x. Can you all see this? For any xy, any pair xy, if there is a map from going from x onto y, then cardinality of y is less than equal to cardinality of x using AC. Can you all see this?
Hello, ma'am.
Yes?
Is there some way to prove that statement without the AC?
Without the AC, is there?
No.
No, I don't think so. No.
Okay.
And with the AC, I suppose you can see. This it is like this with the AC that okay, there's a map x and y. There's a map going from x onto y. So for each element of y, you look at f inverse y, that is non-empty, and from that pick a point. Call that gy. So now I get a map 1 to 1 going from y into x. That's how. So cardinality of y is less than equal to now cardinality of x. So that is what I am using here. That since cardinality of xi is less than cardinality of yi, I cannot get a map from xi onto yi. So this, look at g, then look at the ith coordinate. This is not a map going onto yi. Some point will be left out. Okay. Now, again using AC, you get a point from each yi minus pi I gxi, and then you string them together and get this u in the product. This product. Okay. Then, now look, the ith coordinate of u is outside gxi. So this u cannot be in the range of g. If it was, it would come in gxi for some I, and then the ith coordinate cannot be outside pi I gxi. Is that all right?
Yes, ma'am.
So, yes, yes. Any doubts? You want me to clarify anything?
No, ma'am. I said it's all great.
Huh?
No, I said this was okay.
Oh, you said this is okay. So actually, then we have proved this result, right? All right. So now we'll go into cardinal arithmetic. we give this now, we give these cardinals symbols like lambda, mu. You already know that for any set with n elements, its cardinality we are calling n. Cardinality of the empty set we are calling 0. And cardinality of the natural numbers or any countably infinite set we are calling aleph naught. Okay, I don't know whether I mentioned it, probably not, but the cardinality of reals is called C. And so these are some few names that we already have fixed ones. Okay. And now take two cardinals, lambda and mu, and let us define what we mean by adding them, multiplying them, raising them to the power, and so on. Well, since we have already done it with sets, it was simple. Now, to add them, what you really want to do is you take x and x with cardinality lambda, y with cardinality mu, disjoint sets, and then take the union, take the cardinality. So, to make sure they are disjoint, here, I can put x to be, instead of x, x cross 0, instead of y, y cross 1. Then I know for sure they are disjoint sets. And then union, cardinality of the union, I call lambda plus mu. Multiplication is even simpler. You just take the product of x and y. And, okay, since I have already talked of x to the power y, its cardinality is lambda to the power mu. Okay. And I can do, again, in the standard way, infinite sum and product. Okay, infinite product is nothing, just you take the product of the infinitely many xi's and take the cardinality. And infinite sum is, okay, suppose I get lambda to be cardinality of xi. Again, I make them disjoint by replacing xi by xi cross singleton I, take the union, take the cardinality. That is sigma lambda. Okay. And, okay, by these are well defined, what I mean is, see this, I said cardinality of x is lambda. I'll get lot of sets x with that property. So what set x I use here will not matter. It will give me, if x and x prime have the same cardinality, y and y prime have the same cardinality, and x and y are disjoint, x prime and y prime are disjoint, then x union y and x prime union y prime have the same cardinality. Because you can put together the two bijections, the one from x to x prime, one from y to y prime, and get a bijection from x union y to x prime union y prime. Similarly with product, similarly with power. Okay. And these properties, standard properties, are very easy to see. We have anyway done these power things. Some of them we have already done. Like, okay. In proposition 8, we had done these power things. You know, x to the power y into x to the power z is like x to the power y plus z. We had y union z. We had done such things.
Ma'am?
Yes?
Can you please explain the last slide, like the slide number 20? I got disconnected in between. I mean,
Slide number 20. Which one is it?
Yeah.
Which one? This one?
Yeah, I don't know. Something happened.
This the one? Okay, this is the one. Acha.
Yeah.
So this is what you want to explain? That
Yes,
this is definition of addition and multiplication of cardinals. So I want to add lambda plus mu. And what is lambda? Lambda is cardinality of x, mu is cardinality of y. So what I do is I take two disjoint sets for xy. Or in other words, I take a disjoint set of cardinality lambda and, I take two sets disjoint, one of cardinality lambda, one of cardinality mu. Take the union. And cardinality of that is lambda plus mu. By definition, I call it lambda plus mu. Is that clear? And if you do it with finite sets, you will see that it agrees with your usual definition. Suppose X had M elements and Y had N elements. If I took two disjoint sets, one with M, one with N elements, and put them together, I would get M plus N elements, right? So that is the reasoning behind giving this definition. That all right?
Yes, ma'am.
And for multiplication, similarly, I take the Cartesian product of X and Y, and its cardinality I call lambda into mu. Again, you think of finite case and you will see that it agrees with your usual definition.
Ma'am?
Hello,
Yes.
ma'am.
Yes. Yes.
Yeah, ma'am. I want
Yeah.
to ask, like, here we have taken, if necessary, we can assume X intersection Y is empty.
Yes.
So
Yes.
if it is not the case, like this X intersection Y is non-empty, then
You take sets like this. You take two disjoint sets with the same cardinalities. It is said how you do it. Suppose X intersection Y was not empty to begin with. Then replace X by X cross 0. Call that X prime. That also has cardinality lambda.
yeah.
Replace Y by Y cross 1. That has cardinality mu.
Yes, ma'am.
Now these two sets are disjoint.
Yeah.
Now you take their union.
Okay.
If they're not disjoint, if there's an overlap, then it may not work. One of them may be contained in the other.
Yeah, that's also true.
So it may not work.
So if like overlap, like if X subset of Y, then the cardinality will be the addition will be the cardinality of another set. Is it so?
No, if X see addition, you can't do unless you make it disjoint, right? Just think of finite cases. I take a set with M elements. Inside that, I take a set with say M minus 1 elements.
Counting.
Then you are double counting kind of. You are taking the union. I should be getting 2M minus 1 or something. But I'm not getting it because the same element I'm counting twice.
Okay.
Are you getting that?
Yes, ma'am.
Oh.
Hello, ma'am.
Yes.
If these same definitions are applied in the finite case, you get the usual addition and all.
Yes, that's right.
So this is basically like an extension.
Yes, that's
right. To the infinite domain.
Yes, that's right.
Okay.
Yes. To infinite sets really. Okay. That is right. And similarly, infinite sum and product also. All right. Do you want me to explain this further? Whoever asked for this slide? Or are you satisfied now?
Okay, ma'am.
All right. Okay. Now, these usual things, okay, you can see. Because X union Y and Y union X is the same set anyway. And X cross Y and Y cross X, there's a one-to-one match between them. So lambda plus mu and mu plus is equal to mu plus lambda for any cardinals. Lambda into mu is mu into lambda. Then associative law. Okay, that's because again, union of sets is associative. And so is product of sets. Okay. And this we have already seen. Lambda less than equal to mu and mu less than equal to mu implies lambda less than equal to mu. Right? I talked of that when I was calling them mod X and mod Y. Saying that, if you combine two injections, okay, I had said it anyway, so I won't again say it unless somebody wants it. And this power, okay, we had done that, x to the power y into x to the power cross x to the power z was x to the power y union z if y and z are disjoint. That gives you lambda to the power mu into lambda to the power mu is lambda to the power mu plus mu. Okay, then this one, x to the power y to the power z, that's the second one. And this, of course, we had the power set of x is 2 to the power x. That also we had done. There's a one-to-one match. Okay. So it is just the same. Okay, it was proposition 8. Yes, there we had done it.
No, no,
Oh, that was not proposition 8.
no,
Sorry.
no, that was simple.
Okay, okay, okay. Okay, that was not proposition 8. Proposition 8 is this. Well, just a minute. Okay, okay, okay. This was not proposition 8. Sorry. Proposition 8 is this. Lambda is less than 2 lambda to the power lambda. And we had already done that also. We have done that cardinality of x is less than the cardinality of the power set of x. That is proposition. Okay. And
Cardinality of power set element 1 to the
yeah, sorry. Is that what?
yeah,
That is what I said. It's
no,
okay.
that is not what you said. Power set X.
I had already. Okay. Okay. And this also we had done. I remember we had done it with mod x and mod y. That's all. And it was Cantor, Schroeder, Bernstein, Dedekind theorem. All right, everyone.
Ma'am, this is unrelated to this slide. Still,
Yes. Say.
I'm still trying to find out where you said that, like, if you know, a subset of an infinite set is also infinite, then you know what to say. I mean that the subset should. I mean one of the subsets should have the same cardinality as
Oh,
the
yes,
original
yes,
set.
yes, yes, yes.
That one. I mean,
Yes.
I'm not able to find that out where you showed it.
You are
What-
not able to find out where I showed that.
Yeah.
Okay, let me try to go back.
Ma'am, in the last class, it was the last theorem that you have proved.
Yeah, it was either theorem 10 or 11, somewhere near there.
Okay, ma'am. Okay.
Yes, it is.
Just before this, it's theorem 11.
Probably, huh?
This one.
This one? Oh,
Yes, I'm here. If a like cardinality
this is it.
is X,
If then the if possible. Is this it? Okay, let's see what is the result. Wait. Is this it? If both A and B are less than X, is this the one or is the previous one you're asking?
in this theorem, we have proved like we have used the statement in the proof somewhere in the next slide.
Let's see.
I mean, we have used the statement. I know. I mean, I'm just not able to find out where it was.
Okay, what is
proved.
the statement? Tell me, I can probably hopefully find it.
I
What
mean,
is the
one of
statement?
the subsets of an infinite set. I mean, this
Ah.
was the thing. Like one of the subsets of an infinite set should have the same cardinality as the, I mean, original set.
Oh, I see. I see.
Sequence
Okay.
data point.
Okay. One of the subsets of an infinite set should have the same cardinality as the infinite set. Is that what you said? That means if I have A and X minus A, X is an infinite set, then either A or X minus A have the same cardinality as X. Is that what you are saying?
Yeah,
Okay. All
Yeah.
right. So suppose, okay, the cardinality is less than equal to cardinality of X, I suppose is clear to you, right?
Sorry, ma'am?
Cardinality of A, if A is a subset of X, cardinality of A is less than equal to cardinality of X. That is clear?
Yes. Yes.
Okay.
Yes.
So cardinality of X minus A is also less than equal to cardinality of X.
Sure.
Okay.
Sure.
So suppose now both are less than cardinality of X.
Yes.
Both A and X minus C. Then what I claimed is that the union is less than, union cannot be X because the cardinality of the union becomes less than cardinality of X.
Yeah. Okay.
Okay.
Mhm.
So
Hello?
now what is the cardinality of the union? If A and X minus A are infinite sets, one of them is less than equal to the other. Say cardinality of X minus A is less than equal to cardinality of A. Which way it goes doesn't matter. Then the cardinality of the union is the same as the cardinality of A, of the larger one. This is it.
Okay.
Look at this.
Ma'am, which one?
If A less than equal to B, there's a previous statement. Because I said if A, cardinality of A is less than equal to cardinality of B, then the cardinality of the union is also less than equal to cardinality of B. That's what I had said. So that is a bit previous.
Yeah. Okay.
Just a minute. Let's see where it is. Here, if A and X are disjoint and cardinality of A is less than cardinality of X, then the cardinality of X union A is same as the cardinality of X. Here is this proof. This is the thing.
Yeah.
Okay.
Ma'am, I've understood it.
Have you?
Yeah.
Okay. So, all right, you're satisfied now?
Yes, ma'am. Yeah.
Okay. All right. Now let me go back to what I was doing. Where was I? Slide 20, perhaps.
Ma'am, 21,
Okay.
huh?
Slide 21. Okay. So I was here. So here there's nothing to say, right? Then these are simply things I had done with mod X and mod Y, right? Okay, it's also mentioned that, okay, this one is Cantor, Schroeder, Bernstein, Dedekind theorem, and that one is proposition 8. Okay. Now this also I had done, I remember. For any infinite sets X, I take two disjoint copies and take the union. I'll get this, the cardinality will not change. X cross X cardinality will be same as cardinality of X, right? That I had done. Okay. And okay, one thing I just wanted to tell you that, even the usual things work out. There's a meaning to 2 lambda, right? 2 lambda has a meaning here, a separate meaning from lambda plus lambda. It is 2 into lambda. That is, it is the cardinality of 0, 1 cross X. Because 0, 1 has cardinality 2. But that is exactly the same as lambda plus lambda, right? Because it is union of two disjoint copies of X. Similarly, lambda square has a meaning, set of functions from 0, 1 to X, cardinality of that. That you will find is the same as lambda into lambda. So even our usual meanings, that will not give trouble. All right?
Ma'am,
Yes.
does this mean that we cannot treat these lambdas as, just numbers? We'll have to treat them as sets in order to get a feeling of that. If we treat them as numbers, then
no, they are numbers, all right. You can think of them as numbers or sets. It is all the same. But the thing is that they are not numbers, they are not the natural numbers, right?
yeah.
So we don't know their properties. So in a way, perhaps you are right. You have to think of them as sets for that. Or you have to think of them as a different kind of numbers, different kind of elements. Because, see, we have to see that the properties of natural numbers, not everything goes through. For example, no natural, and for a natural number you would not have, unless it is 0, you will not have n plus n equal to n. Right? But for infinite cardinal numbers, lambda plus lambda is lambda, right?
Yes, ma'am.
So that's why you have to be with these. They are numbers, perhaps you can think of them as infinite numbers, as different from your usual numbers.
Okay.
They are sets also. This is, of course, that Koenig's theorem that I proved. That's all. That if lambda I is always less than mu I over a family, then sigma lambda I is less than pi mu I. And anyway, lambda less than 2 to the power lambda we've already done, so I don't know that it comes in here all that much. Okay, so so now you have any doubts, anything you would like me to go over again? Anything? because more or less we have covered things. So we'll discuss exercises and things and doubts. So what would you like me to go over particularly? Anything, anybody? Or any doubts? Have you all followed more or less what is happening?
Hello, ma'am.
Yes?
Can you define functions on these cardinals like you define functions on the natural numbers?
Yes, you can define functions. How do you mean? On all cardinals?
Yeah, on all cardinals.
Well, okay, you can define them, but yeah, it does not form a set. I was hesitating whether you know what that means. There's some technical things there. You can define them, yes, but it forms what is called a class and so on.
Ma'am, so I was saying if you accept the existence of a class, like in there's some other set theory.
No, we accept that existence anyway in any set theory. Okay.
Yeah, so if you do that, like, can you extend the usual functions on N to the set of cardinals? Or something?
How do you mean? What usual functions?
No, like I'm saying, will you get something interesting if you do that?
Well, I'm not aware of it. Maybe
You will get classy.
No, he's not saying that. He's saying something else about extending the functions from N to something, and can you get interesting functions, something. I do not know.
Can you repeat your question again?
You have functions on N, right? So
Yeah.
is there will something interesting happen if you extend any special function on N into the set of class of cardinals or something?
No. First of all, let us keep class aside for the time being. You see, Vivira will teach you and he will give you a set corresponding to each cardinal. Like he gave for n 0, 1 to the power 0, 1 dot n minus 1. For LF0, he gave you the set of all natural numbers. Right?
Yes,
Similarly, for each lambda, he will give you a set, very specific set. Okay?
Yes,
now,
sir.
on that set, on each of these lambda, if you think of it as a set, they are very, very interesting functions. Okay?
So I did not get the last part.
I'm saying that if lambda will be defined as a set, each lambda. Now you fix a lambda. Like you fix natural numbers. You fix lambda. Now you are saying that, is this set interesting?
No. I'm saying,
are there functions, interesting functions on this lambda? That is what you are saying.
No, I'm saying, are there interesting functions on the collection of all lambdas? Like that is a class.
Precisely. Now there is a technical problem. Because the collection of all cardinals is not a set. It is a class. Now, it is true that there are cardinal functions, meaning that there are functions for each cardinal. To each cardinal you associate a interesting function. Yes. And they will not be a function in the usual sense, because a function is in particular a set. Amit Kuber was telling you that what is the definition of a function? A function is a set, okay, whose each element is a... So first of all, it is a set whose each element is a ordered pair, and for every x there exists at most one y, such that the ordered pair xy belongs to F. Okay?
Okay.
That is the general notion of a function.
Yes, sir.
Now, if you stick to the definition that a function has to be a set, then the answer to your question is no. On the other hand, on the other hand, suppose we have already seen a function, lambda going to 2 to the lambda.
Yes.
Okay?
Yes, sir.
So this, in your mind, will be a function on the set of all, on the collection of all cardinals. Lambda going to 2 to the lambda.
Yeah, that will be a collection of functions.
No. now you are saying that your domain is the collection of all cardinal numbers.
Yeah.
So on that you want to define a interesting function.
Yeah.
So I'm saying on that collection
Okay,
of
okay,
all
okay.
cardinals, I'm
Okay.
defining a function.
Yeah, lambda going to 2 to the lambda.
Lambda going to 2 to the lambda.
Yeah, yeah.
Okay, so like this kind of thing you can definitely talk of,
Yeah.
but in a strict sense, it is not a function, it is a class.
Yeah, yeah. I get it, sir. I get it.
Okay?
Because the domain is a class.
Because the domain is a class.
Yeah, yeah.
Because a domain, because a class may also satisfy the property that all its collections, all its elements are ordered pairs, and for each set X, there is at most one Y, so that ordered pair XY is in that class.
Yeah, but you will have to call it by some other name, not function.
No, we call them a class.
No,
Actually,
he's
okay.
saying you can't call it a function.
Okay,
no,
okay.
what happens is that we call it a function, but we are alert. Ah,
Yeah, yeah.
we are alert that this is function is not that strict sense that it forms a set.
Yeah.
It is a class function.
Yeah, yes, sir.
You understand? For
Yes, sir.
example, I will tell you one more interesting cardinal function. Viveka
Sure.
will show you that
Yeah.
given any cardinal number lambda, she is not in a position to show at the moment. For
Okay.
any given cardinal lambda, there is a cardinal which is bigger than lambda and which is least such.
Oh, okay. The least cardinal bigger than lambda.
Right.
Oh,
But you have to prove the existence,
okay.
which Viveka will show.
Okay, okay, sir.
So we call it lambda going to lambda plus, lambda to the
Oh.
power plus.
Okay, sir.
Okay, successor cardinal.
Yeah, yeah.
Okay, that is also a function in the sense that you are thinking.
Yes, sir. Yes, sir.
Okay,
Yeah.
but the graph of this will not be a set.
Yeah.
It will be a class.
But then you can, if you restrict it to a set, it becomes a function, right?
Yes. In fact, the thing is the following. If you intersect a class with a set, it becomes a set.
Oh, okay.
Okay?
Okay, okay, sir.
Huh?
Yes,
That
yes.
is one of the thing called subset axiom.
Oh, yeah, so now it makes sense actually.
Okay.
Yeah, yes, sir.
So here is a thing that lambda going to lambda plus. Now you have been considering collection of all sets.
Yeah.
How about x going to power set x?
Yeah, that's also a class function, right?
Yes.
Yes.
Okay.
Yeah,
And
yes,
in
sir.
fact, Viveka will teach transfinite induction and such. You can do transfinite induction on the class of all ordinals.
Oh, okay. You can actually do induction or transfinite induction on a
Yes,
class.
so you can almost treat classes like sets.
Okay, sir.
Except that you should be conscious
Yeah.
that they are not sets in the as if it is a member of the universe of sets.
Yeah,
They are
I get
classes.
it. Yeah, yes.
They are only expressed by their formula.
Yes, sir.
Okay, there are many. In fact, set theory is actually the game of cardinal numbers.
Yes, sir.
Okay, and so there are lots of things, very intricate things that you have to handle. Okay.
Yes, sir. Thank you, sir.
Excuse me, sir.
Okay, so that was a nice discussion. Interesting one.
Excuse me.
Yes,
Just one more question regarding this discussion.
yes,
The statements are made that the collection of all cardinals is not a set. Does that have
yes.
something to do with Russell's paradox by any chance, ma'am?
What did you say?
Does that
Does it have anything to do with Russell paradox? Huh? Now the point is the following. Let me tell you one thing. Suppose you can prove it very easily without using Russell's paradox. Suppose the collection of all cardinal number is a set. Okay?
Yes, sir.
Call it X. Now, I am giving you a cardinal number which is bigger than all these cardinal numbers, namely cardinality of the power set of X.
Yes, sir.
So I can always produce, if you give me a set of cardinal numbers, set, then I can always produce a cardinal number which is bigger than all the cardinals belonging to that set.
Yes, sir.
Okay?
Hello, sir. Hello, sir.
Yeah.
Sir, here you were able to take the power set only because it was a set, right?
Because
So that-
by hypothesis it was
It
a
is
set.
yeah. But if it's a class, you can't do it. That's
No,
how. Yeah.
No. Okay.
Yeah.
So here showing what question that he asked, it has nothing to do with Russell paradox. Okay. It is
So,
just a theorem that which you can prove that given a, I have given you the proof that given a set of cardinals, there is a cardinal which is bigger than each element, each cardinal belonging to that set.
Yes, sir.
So there is a cardinal lying outside.
Yes, sir.
And that is just comes from the theorem that cardinality of X is less than cardinality of 2 to the X.
2 to the power X.
Okay.
Okay, sir.
So anything more?
Excuse me, ma'am.
Yes.
So now that you're taking up the questions, there is a comment on YouTube live
Yes.
requesting you to repeat the arguments of second page of theorem 11, the proof
Second
of
page
theorem
of
11.
theorem, proof of theorem 11. Okay.
Yes, yes.
Theorem 11.
Yes. Cardinality of X cross X is same as cardinality of X for any infinite X. Okay. So I suppose this, okay, that if suppose X is A union B, then both A and B cannot have cardinality less than X. Okay, I did that a bit earlier also. So I suppose that would be acceptable. And
I think
yes?
it was for the second page.
Second page.
Okay.
I think the first
all
page
right.
is clear.
Okay,
the second
okay.
page is
All right. So we'll just go quickly through it. I know what is the thing, that construction.
Sure.
All right. So suppose okay. So we look at all AFs where A is a subset of X and F is a bijection from A cross A. And I take infinite A's just to make things simple. And I define a partial order on this set. This is first of all non-empty anyway, because if I take any countable subset of X, X being infinite has countable subsets. If I take any countable subset of X, then there will be an F going from A cross A to A bijection. We already know that. We have proved that. So this will be non-empty, and I define a partial order on it by, well, BG comes after AF if B is larger than A and G extends F. And if this B confused people because I used B later on in the proof somewhere. So instead of this BG, if you call it CK, that will not matter. CK will be larger than AF if A is contained in C and K extends F. And this is a partial order. You can use Zorn's lemma on this because it satisfies the usual conditions. You can check and get a maximal element AF. And then if this cardinality of A is the same as cardinality of X, that is good enough. Because that means that there is a set A of cardinality same as X, such that from A cross A to A, there is a bijection. And since this is a cardinal, and since X and A, there's a one-to-one match now, because the cardinality of A is the same as cardinality of X. So from x cross x to x also there will be a bijection. You can convert it. All right. So if possible, suppose the cardinality of A is less than x, then cardinality of x minus A must be equal to x. They can't both be less than x. Then inside x minus A, there will be a set B of cardinality same as A. Okay. Then, all right, since these are all infinite sets, you can break B into 3 parts, disjoint, all of the same size as B again. We have done this before and call it B1, B2, B3. Now here I suppose is where the problem is, because it's just computation really. If you write it down, whoever you are, you will see it. You see, I have a bijection A cross A to A. I had it. Now B is the same size as A. So that means from B cross A to A also I can get the bijection. By B1. I didn't know. From B cross A to A also I can get the bijection. How? By first going from B to A, and then B cross A becomes A cross A, and then I go to A. Yes, but from A to B1 also I have a bijection. So from B cross A to B1 I have a bijection. If you accept this, then A cross B to B2, B cross B to B3, by similar arguments, I have a bijection. And why am I doing it? That is because, look at A union B cross A union B. What is it? It is A cross A. And, and I write B as B1 union. No, sorry. Look at A union B cross A union B. What is it? It is A cross A union A cross B union B cross A union B cross B. And AB are disjoint. So this A union B cross A union B is broken into 4 disjoint parts like this. And from each part, I'm getting a bijection. F goes from A cross A to A. F1 goes from B cross A to B1. F2 from A cross B to B2. F3 from B cross B to B3. And that means I get from A union B cross A union B this bijection to A union B, and it extends F. So this thing here, A union B, comma, F union, F1 union, F2 union, F3, is something in your partial or ordered set P, which is larger than A. And this contradicts the maximality of A. AF was a maximal element there. So this is the contradiction I get. So that means I cannot have cardinality of A less than X. That's how I got the contradiction. So cardinality of A must be X. Okay. I hope that this will clear it.
It has not yet come.
Yeah, I assume that it must be clear to the person whoever asked. So thank you so much, ma'am.
Okay. Anything else?
Ma'am,
Yes.
if like the Schroeder-Bernstein theorem, we make the
Yes.
following statement: like
Yes.
there are two groups G1, G2, and G1 is isomorphic to a subgroup of G2, and G2 is isomorphic to a subgroup of G1. Then can we say that they are isomorphic?
No, probably not. Because what you put together like this may not be an isomorphism.
Not be a homomorphism.
May not even be a homomorphism. What we have put together is not keeping the structure, right? We are putting together two maps.
No. I'm just saying like the hypothesis.
Can we prove this?
Yeah, can we? Is this result there?
No. No, it's not true. Do you know the counterexample? By the way, there is a counterexample. Do you know it?
Yeah. Okay. Let me change your question slightly. Okay. Let us go to topological expression.
There's a nice counterexample.
Suppose X is homeomorphic to a sub X and Y are topological spaces. Suppose X is homeomorphic to Y,
To a subspace
to
of
a
Y.
subspace of Y, and Y is a homeomorphic to a subspace of X. Will that imply X and Y are homeomorphic?
What do you say? First, let's give him a chance. What do you think?
I will think.
Can you repeat the statement again?
Oh, suppose X and Y are topological spaces. X is homeomorphic to a subspace of Y. Y is homeomorphic to a subspace of X. Are X and Y homeomorphic? You know, changing from groups to topological spaces, your question.
Oh, I don't think it is true actually.
It is
because
not
if we take open interval and closed interval.
Yes, that's it. That's it.
So
Yeah.
in set theory, you have no structure to take care of.
Yes.
Okay. Whereas here, in these kind of questions, there are structures to be taken care of also.
Yeah. So in groups also there is some counterexample.
Well, it does not imply that this does not imply that there is a counterexample.
Probably there is,
but I think I have seen it.
Okay.
During this course, if I can remember, I will tell you. Okay.
Okay, sir. Thank you.
Just remember one thing, that set theory is also called a structureless topology, a structureless mathematics.
Yeah.
And people think that, oh, there is no structure, what is there to play with? That is far from wrong, far from correct. Because you look at already, we are playing just with the one-to-one and bijection maths.
Yeah.
Madam, all that she did was a game of one-to-one and maths and bijections. Okay? And so many things we could do.
Yeah.
Okay? All these theorems have such an interesting argument. You require intelligence to prove all these things.
Yes.
So saying that structureless mathematics is not interesting, well, I do not subscribe to that, because less structure you have, more challenges you have. More challenges you have. So from a mathematician point of view, less structures you have, to establish a theorem, big theorem, you require a big challenge. And that is what is challenging. You have more structures, then you have more things to play around with. And then, of course, you can prove many more results. That is sure. But if you take mathematics as a challenge, then all these things, set theory, descriptive set theory, because we are having much less at our hand to start with, and with that we are going ahead and proving many things. Logic also hardly starts with anything, but then it once it develops a general machinery, it just hits things like hits mathematics at various places, which general mathematicians cannot do. Yeah.
Yes. Yes. Anything else? I think generally, anybody wants to discuss anything, we can do it now, because all we are now looking at are exercises. Yes, this is sort of trivial, isn't it? We've already kind of done this. So you can try this. Lambda plus, if lambda and mu are infinite, then lambda plus mu is maximum lambda mu. And since it's same as lambda into mu.
Then we that we can forward it so that afternoon can look at the
YouTube.
No, then to them also.
Not forwarded. I don't understand. What are they
Okay,
supposed to do?
So I'm addressing it to the organizers, my question. You see,
So,
there are a lot
this
of
is-
exercises written here. Some was added yesterday night.
Okay.
Now, can we forward this mail, this file to the organizer, and can they post it on the website so that the students have a look at the problem before coming to the tutorial? This is
Hello.
what Amit. This
Hello.
is what.
Yes.
I'm
yes.
here. Yeah,
This is
I'm
what
here.
Amit. This is what Amit did for his tutorial.
Oh, that would be good. Then they can
Yeah,
really
I'm
see
here.
this.
SMS, I'm here. You can send it to me. I will upload it.
Okay. Okay. So
Yeah.
it can be done only after this lecture. This computer.
Yeah.
Okay. So I will send it to you, Amit, immediately after the time is over, so that the students in the meantime can think over.
Yeah.
And then the lecture, then the tutorial will be worthwhile. They will have some realistic chance to take this. But this they should be able to do.
Yes. So I hope you have all heard it, all of you students. But the exercise 1 you can try right now. Try. Anybody give ideas on it. Yes. Anybody?
I mean, we
Ma'am,
used something
Yes.
similar,
since
I think.
Yes.
Like lambda, lambda plus lambda equals lambdas.
Yes.
So I think we'll need, I don't know, I think we'll need this one, like lambda plus lambda equals lambda and mu plus mu equals mu. And I think we can work from there. We will,
well, I don't
manipulate
exactly
these
see, but you can try. Try.
Ask them to assume
Try.
lambda less than equal to mu.
But you can assume one of them is, you can assume lambda less than equal to mu or something if you like.
No, I was like, how to couple lambda and mu. So I thought maybe we can use these two equations, that lambda plus lambda equals lambda. And mu.
Just give a thought. You have to use that, but give a thought, because assume that
Yes,
lambda is less than equal to mu.
Somebody is saying yes.
So if you consider two sets x and y with cardinality lambda and mu, so you consider x cross y, x and a set of all functions from x to y. These are they give you the cardinality of the cardinal numbers we want to work with, right?
Set of all functions from x to y. No. That is y to the x. That's
Hello.
mu to the lambda. Yes.
Ma'am, if you assume that mu is less than lambda is less than mu.
Yes,
then if
you can assume. Yes.
Yeah, you have the theorem that if the set A has cardinality less than cardinality B, then A union B has the same cardinality as B, right?
Yes. Okay.
So you can use that to prove that lambda plus mu is equal to mu, right?
Okay. Okay. Yes. Right.
Same thing for
Yes, same thing, similarly. Yes, you can. And by the way, don't say less than equal to, say. After all, lambda could be equal to mu.
Yes, ma'am.
So say less than equal to. And by the way, I don't exactly know. Maybe this is not in the exercises, but have you got that lambda less than mu, then lambda plus mu is less than mu plus mu, those things?
That was not there earlier.
No. Achha, then I will.
That was not there earlier.
No, that was not there. That was not there.
Yeah.
Then that's not what I mean.
Then which one?
Okay, so I will add a few things that I think is not written down here in the exercises. That is, if lambda is less than equal to mu, that lambda plus mu is less than equal to mu plus mu for any cardinals, lambda, mu, nu. And lambda into mu is less than equal to mu into nu.
That one.
I will add these. I cannot write down right now, but I'm telling you.
Hello, ma'am.
Yes, so you try to prove those also, yes?
You just said like two statements now, right? Do those statements directly follow from exercise 1?
What did you say?
You said two statements now, right? If lambda is less than mu, then lambda plus mu is less than mu plus mu.
Yes, I think I said less than equal to.
Yeah. So I'm saying this statement follows directly from exercise 1, right?
Okay. I don't exact. Can you say how it follows? I didn't quite get what you were saying.
Ma'am, because mu plus mu is equal to mu, right? So you already know that.
You do not know the relation between mu and nu. And all you know is that lambda is less than equal to mu.
Yeah, okay.
You do not know where nu comes.
Hello, ma'am.
And then maximum of lambda comma mu is there, right? You can use
maximum. Yes, okay.
You see, this may be just one intervention. They need not be finite. They need not be infinite.
No, they need not be infinite. That also I said.
That also you have to keep in mind.
I said any cardinal number.
Okay.
Yes.
So can we do it separately when it's infinite, when it's finite?
No.
You can if you want to, but try the simple-minded way.
But then you will have a problem when one is finite and another is infinite.
Oh, yeah.
And try the simple-minded way.
Okay, ma'am.
Simplest you can think of.
Excuse me, ma'am.
Yes.
Ma'am, are you talking about exercise 1 that it holds for both finite as well as infinite cases?
No. Exercise 1 is infinite. I spoke out an exercise which is not written here. I said suppose.
Make it slightly.
But let me finish what I'm saying. Suppose lambda is less than equal to mu. Lambda mu nu being cardinals, then show that lambda plus nu is less than equal to mu plus nu is what they said.
Okay.
Something more he has to say, yes.
By the way, in exercise 1, you make the hypothesis lambda, mu are cardinal numbers of which at least one is infinite. I am not demanding both are infinite. Okay, then also it is true.
Okay, this is different. This is a different one. This is just exercise 1. What I said was a different one. And what I said was that if lambda is less than equal to mu, lambda mu nu being cardinals, then lambda plus nu is less than equal to mu plus nu. Lambda into nu is less than equal to mu into nu. Lambda to the power nu is less than equal to mu to the power nu, and so on. Nu to the power lambda is less than equal to mu to the power lambda. This is what I asked. And this is very simple, really, if you just give it a thought. All right. Okay. So, okay, now look at exercise 2 also and see whether that is simple. Okay, first look at nk for k greater than equal to 3. 2 you have already done. Can you show that that is countable? Do you have a simple way of showing it?
Hello, ma'am.
Yes.
We can use induction, right?
Yes. Okay. You can use induction. What about the set of rational numbers?
You tell the speaker, organizer to forward.
What about the set of rational numbers? Can anybody say whether that's countable?
We can consider the set of rational numbers. I mean, as a subset of the set n square. Like
as
considering the numerator and denominator as a tuple of two natural numbers.
Yes. What? Say that again. Say it a bit slowly. Yes, you can consider it as a subset of
n square. I mean z square.
Subset of z square. Considering how by how exactly will you? That's right. You will take the numerator and denominator.
Yes,
but okay,
so
okay,
to
okay, okay,
ensure
okay.
that
You
we
are taking
don't.
it as a subset. Okay, okay, okay. All right.
Yes, ma'am.
Okay, okay.
So it is an infinite subset of a countable set. So it will also be countable.
Okay, 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 okay. All right. You mean you match it sort of? Okay, all right. Achha. The set of polynomials in one variable with rational coefficients. That should be what?
Finite.
Oh, sort of all finite. Did that? Oh, sorry, no, you didn't do this. Finite sequences of natural numbers is what exactly? Okay. Set of all finite. Do you understand? All finite, like all m tuples of natural numbers, m varying over again all finite integers, sort of, positive integers. You understand? All natural numbers, all doubletons of natural numbers, all two tuples, all three tuples, and so on. That is all finite sequences of natural numbers. Is that countable, by the way? What do you think?
Hello, ma'am.
It is
Yes.
countable.
Yes. Oh, yes.
You
Yes.
can write this as a union, right?
Yes.
Union I equals 1 to infinity n power I.
Okay,
So
okay.
each of the sets are countable, so the whole set is.
That's fine. 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 Then let us see. What is the next one? All polynomials in one variable with rational coefficients. Well, that's actually, I suppose, you will get it straight away. Okay. Say.
Ma'am, we can think this as like the one I said, like x cross x. I mean, let's say 1x is like x to the 0. I mean, capital X is the set, and I'm considering the basis like x to the 0, small x to the 0, and small x is the variable, and another, let's say, small x to the 1. So that is, let's say, I mean, another
Okay, we fixed a
capital X.
variable small x. There's no problem with that then.
Yes. So then we know that the cardinality of capital X cross capital X, the capital X being a set, I mean, countable infinite set. So the cardinality of capital X cross capital X is the same as the cardinality of capital X.
If
So,
for an infinite x, only. Yes,
yeah.
yes, okay.
Now, rational number set is also an infinite set.
Yes.
And
yes, right.
If you consider let's say the rational coefficients, it would be like the set x. Yeah, the rational numbers as the set x.
Yes.
Then
okay.
all the polynomials would be like x cross x, and so on.
Yeah, I think you are more or less on the right track. Yes, you have to sort of just organize it a bit. I think you are more or less on the right track. Except, you have to take x, x cross x, x cross x cross x, all the
right,
things.
Right.
Achha,
That's what I'm saying.
Okay. Oh, that's what you are saying. Okay. Yeah. That's
and all
the
of that would be equal to cardinality of x.
Okay. And then you are taking the union. You are taking a union, by the way, right?
Union.
Aren't you taking all of them? Each one is x, right? Each one has the cardinality of x, right? Now you are taking all of them together.
Yeah.
How many are there?
I mean, for each, x to the n or x to the I. I mean,
right.
Variable x. Variable x to the I. You consider one capital X set. Capital X is the set of
each
rational
variable
numbers.
x to the I. Wait. You mean you are taking each coefficient as a capital X set at each coefficient place?
Yeah. Like, I mean, let's say I have a x to the 0, a1 x to the,
I see.
a0 x to the 0 plus a1 x to the 1 plus a2 x to the 2.
Yes. Then?
So the coefficient of, this a0 would belong to set x, capital X, rational numbers. Now,
that's just
a1
rational
would,
numbers then. Yes. Capital X is just rational numbers in that case.
Yeah. and A1 would similarly belong to, capital
Yes.
X.
Yes, okay.
Right.
Yes.
So, I mean, in this way, A1 also belongs to capital X, A2 also belongs to capital X, and we can
Yes.
generalize AI belongs to capital X. And
There's nothing to, they are just rational numbers. Okay, all right.
Yeah.
Yes, okay.
So, aren't we taking, the, what to say, the Cartesian product when
Okay,
we are...
I see. Okay, all right.
Hello, ma'am.
Yes, yes.
Is she trying to take an infinite Cartesian product? Because in that case, it will not be countable, right?
Is she trying to take an infinite Cartesian product? Why should it be infinite? Are you taking an infinite one?
I mean, polynomials, are they infinite?
No, of course, polynomials are not infinite. Don't you know what are polynomials?
Yeah, so it's like some x
No,
to the n
polynomials are not
plus...
infinite. I think what he had in mind was the following. Polynomials, each polynomial is not an infinite thing. But then, for all, there are polynomials of all degrees.
Yeah.
So you are running through all possible natural numbers is what I think he is having in mind. So I think
Ma'am,
yes.
No, so she's basically taking the union.
She's taking the union.
Union, right?
Of what?
Or is it the Cartesian product? I think
what?
it's the Cartesian product.
Of what?
Right?
Of what?
No, but you should take the union of all the Cartesian products, right? All finite Cartesian products.
Yeah.
That's it. That's it. That's it. That's right. That's very good. What you said finally, union of all Cartesian products, that's the right one. Did you get it? The one who started first, I don't know your names, yes?
Ma'am, I didn't get how it is union of Cartesian products. I mean,
you didn't get how it is union of Cartesian product?
Yeah.
Okay, it is like this, I think. You take all polynomials, you fix an n. Look at all polynomials of degree n.
Right.
There, and then their coefficients kind of, they match with all n tuples of rationals, kind of.
Right.
Is that what you said? N or n plus 1, I have to think a bit, something like that. Okay, but now this, so that is one xn he's calling it. That is countable, no?
Right. Sure.
Now he is varying over all n, so he has to take union of this over.
Right. Yeah.
That's what he said.
Okay.
And so each xn being countable, union of countable sets is countable. That's what he said.
Yeah.
That's what you said, right?
Yes, ma'am. Yeah.
And do you people know what are algebraic numbers, by the way?
Ma'am, they are like the algebraic polynomials have those as coefficients. I mean, I don't know.
No, polynomials. Which polynomials? No.
Ma'am, it is root of algebraic numbers are root of polynomials with rational coefficients.
Yeah.
Right. So now, after this, can you see that the set of all algebraic numbers is countable?
Each polynomial has finite roots, so...
Yes, very good. Excellent.
Actually, the last problem, isn't it we proved the set of all finite sequences of natural numbers are countable. So instead of natural numbers, if we put rational numbers, that is precisely what the next problem is, right?
Yes, but you have to notice it. It is precisely what the next problem is. But you have to notice it. Yes, that's right. Very good.
Sorry to interrupt you, ma'am. I would like to remind you that you have 7 to 8 more minutes for your
Yes, it's okay. You can stop anytime. Yeah, because we are just discussing now, and we'll continue the discussion in the thing. So whenever it's time, you stop.
Okay.
Now cardinality of this is real numbers denoted by C. I said that orally already. Show that R is uncountable. Have any of you seen a proof of this? R is uncountable, real numbers?
Yes,
so
ma'am.
You
Yes,
have?
ma'am.
Okay, so show us.
Ma'am, we can consider the smaller set 0 to 1, and we will find that it contains irrationals and rationals both, and irrationals inside this uncountable. Since
Why is it
subset is
uncountable?
uncountable.
Why is it uncountable? Wait. That's precisely what I was asking. Why is it uncountable?
So we can do this thing. Like we can start with the set that he gave, 0 to 1.
Yes.
And like.
By the
now
way,
here
just 1 second. Suppose you show that the set 0 to 1 is uncountable. Are you done?
No, I'll have to assert that 0, 1 is a subset of R. In that case, like R can't be countable.
Very good. That's what I wanted to hear.
Yeah.
Okay, continue.
So like here
Yes.
we're working on the
yes.
Can't we find a map between 0 and 1, 0 to 1 to the whole real numbers?
You can, but as he said, it's enough that a subset is uncountable, right?
I mean, it'll be more
Subset of a
complicated that way.
countable set cannot be. It will be more complicated, right?
So yeah, like here we are going by the assumption that we can have a decimal expansion of all the numbers, like all the real numbers between 0 and 1.
Okay.
And now, like assuming we have an enumeration of real numbers, say x1, x2, x3.
Suppose you have an enumeration.
Yes, ma'am.
Yes. Okay.
And let the decimal expansion of xi be 0.ai1, ai2, ai3, etc. Now we can apply Cantor's diagonal process here, and we can construct a new real number such that like we look at a11 and we choose a like number which is distinct, like different from a11, and make that the first digit in the decimal expansion of this new number, and similarly for a22, a33.
Okay, but just one thing. Okay, I get that. And so you are going to get something which you say is not in this countable set, and you get a contradiction.
Yes.
No. The real number may have two.
I was getting to that. You see, but is that expansion of a real number unique?
No, ma'am, it's not unique.
Are you talking about 99999?
Ma'am.
Yes.
I think I've got something like if we prove that all the sequences of zeros and ones, they are uncountable.
Yes, we proved that.
Can we use that? I mean,
well, tell me how you can use it. I suppose.
Like,
just tell me how.
The decimal expansion. I mean, from 0 to 1, let's say. I mean, point 0 point. Then you start your sequence like 0 0 1 1 whatever, and that. I mean, if you like the first, the first member of the sequence, like.
Wait a minute. What are these things now? They are not just. Okay. They are just sequences of zeros and ones. What exactly are they?
Yes.
That is uncountable. You have shown.
Yes.
Now, what are you proving?
I'm trying to prove that this let's say the subset of 0 to 1, open 0 to open 1.
Yeah. So how are you identifying this with the subset of open 0 to 1? I haven't quite got that.
Okay. I mean, okay. Let's consider any sequence of zeros and ones. Right. So we can try to map that with like the decimal. What to say? 0 point something like what to say. Let's say the sequence is like this: 0, 0, 1, 1, something. So our decimal we should consider would be like 0.0011 something.
Oh, you are looking at the decimal expansion. You are thinking of it as a decimal. Just a second. First of all, are they all distinct? Are they all give? First of all, just see that they all give distinct things.
Should be. Yes, should be.
Okay. All right. Okay. I see what you are saying. Okay, that's a good one. This is a neat way. You've got a much smaller set and it's still uncountable. And of course, the whole thing is uncountable.
This is a simpler
nice.
one. Yeah.
Huh?
This
is very nice.
Answer.
This is really nice. Very neat.
Ma'am, I had one doubt. Since we are considering all finite, all sequences by 0 to 1, but in our decimal expansion after 0.1, no matter how many 0 we will put, it will be the same as 0.1, but in our set of sequences that will be a different sequence.
No, wait, all your sequences are infinite. So however many zeros you put doesn't make sense. Either you are going to put 1 or you are going to put zeros.
Right.
It's not a finite sequence.
Right, got it.
Roopkatha, can you repeat your proof?
Sure. I was trying to find a bijection between the sequences of zeros and ones, and the what is it? Some decimals less than what? Decimals less than 1. I mean between 0 and 1. Let's say close 0, close 1, close 0, comma close 1. So what I consider is that one sequence, any one sequence you consider, it starts with like 0, 0, 0, comma 0, comma 1, comma 1, comma something, and we map this sequence somehow to the decimal 0.0011 something. Now we have shown that the sets of all the sequences, sequences consisting of zeros and ones, it is uncountable. Now this set consisting of all these decimals should also be uncountable in that case, right? Am I
Yeah, fine. Yeah, that's a good proof.
I mean, it just popped up.
There's a lovely proof. I think, yes, I think it's more, let's see. Yeah. Okay, I think it is time.
Yeah, it is time, but if there are more questions, then they can probably, you can address
we can
one
do it
or
at
two.
4, no? We can continue at 4.
Then we can do it during the tutorials.
Yeah, because we have plenty of time now because the material is over now. It's just discussions we are having.
Sure, ma'am, sure.
Just,
Amit, I am sending this file to you. Amit, I am sending this file to you by an email.
He's gone, perhaps.
Okay.
I think probably he's gone. Yeah.
Okay.
Anyway, he has already said to send, so send.
Yeah, sure. Okay. Thank you so much, ma'am. So we'll break for 15 minutes and get back at 11:45 for the next lecture. Thank you.
Okay, next.
Sorry, sir.
It's Who's talk?
Amit Kuber's talk.
Hello, SMS.
Yes.
Yes, so done.
Grazie.
I know
Okay.
you spoke in Italian.
Huh?
I know you spoke in Italian. Grazie.
Yeah. I show off a lot.
Danke.
That's German.
Merci beaucoup.
That's French.
Yeah.
What happened? It's not coming. No. I have to go here. So first, let me. What happened?
How is it still there? Oh, because it's going.
Okay. So I have I missed this part. Let me see.
What do you mean? Oh, you haven't phoned Pramod, I hope.
No, I
Because
am
tomorrow
good.
I cannot.
You?
Because Parul is taking off tomorrow.
No, I have
There's no
not.
time. Right. That's the only way. Parul is taking off, and I also go away. Then how will things be? You have to go.
Wait. Can you somehow close this, because I am not able to get out of my. Okay. Maybe I can. I can sign. Where are you? I don't see you.
Are you talking to me?
Yes, I don't see
Oh, yeah,
you.
yeah. I'm here.
Oh, acha.
Yeah.
Unfortunately, I have to get ready, take bath and eat and all that.
Yeah.
So I will be missing your lecture.
No problem.
But what I will be doing, oh yeah, that's the answer. Z square and Z4. Whoever asked that question, did somebody ask about group? Oh, no. That is a different question. No. Somebody asked a question about if there is a isomorphic paper. No, still I don't have the answer. Okay.
Yes, sir. I asked it. I think this example by Nidhish works. The one he has written in the chat.
Where has you written? 2Z? No. 2Z and Z are isomorphic.
No, sir. So that construction, that H cross G so many times and G cross G, these two, where you can take H equal to.
Wait, just a second.
Okay.
Just a second. Say that again.
Yeah, so the examples he have given is G1 is G cross G for some fixed group G, and G2 is H cross G for some H subgroup of G. Here you can take G equal to Z mod 4 and H equal to Z mod 2 sitting inside.
Okay. So there is a yeah, because here it is this construction works. Oh, acha. This construction is here. Acha.
Yes.
Okay. But why cross you don't do? It gives the impression of a direct product.
Direct sum you should take.
So if you take the direct sum also,
Yeah.
then thing is that H is a subgroup of G which is not isomorphic to G. You take that. We take that. And then this will work if you with the direct sum.
Yes.
Okay. Yeah. So this is a structure-like mathematics, but it works very well. I mean, there are lots of set theory is a very, very challenging subject. Very, very challenging. No, I have to go. I have to take bath. I have to get ready, and so I will be keeping it on both the loud so that I am hearing while I am shaving and this.
Okay. Okay.
But I will not be present all the time. I know
Sure.
what you are going to do. You are going to do now ultra product and all that.
Hyper reels.
I
will do non-standard reels.
Okay.
Yeah.
That right. By the way, I have little doubts about what BB Rao was doing for finite axiom choice. I thought this was going to be his talk.
No, this is my talk. So he is not speaking when.
I thought that because yesterday BB Rao didn't speak. But let me ask you, is Sujata also around or not?
She is around somewhere. Yeah.
Let me ask you, you see what he is doing is that given finitely many non-empty sets, x1, x2, xn, he introduces finitely many new constants, a1, a2, an, and the axioms a1 belongs to x1, a2 belongs to x2, an belongs to xn. Okay? And then he says that, well, this has a model. And take this to the Germelo-Frankel axioms. Add it to this. And then he says this as a model. And in the model, the interpretations of A1, A2, An will be the choice function for x1, x2, xn. But how do you prove that? How do you prove that this is a model?
No, I think I will need some time to think about it, and it's already time for my lecture. I will start.
Okay.
Yeah. Is the host around?
Yes, sir.
Yeah.
Let me start recording. So I hope everybody is back from break. Okay, so let's begin with the next session. I welcome Dr. Amit Kuber for continuing his lecture on predicate logic. Over to you, sir.
Thank you. So, first I would like to ask if there are any questions. Some people commented yesterday that I was a bit too fast. So please tell me what I need to cover.
Hello.
If there is, yes.
Hello, sir. I just want to I have just a small doubt. Can you please repeat this zero-array relational symbols are proposition from proposition logic, like in the FOL language? Can you just elaborate this again, please?
Sure. So a zero-array relation symbol, as you will see here, an M-array relation symbol will be interpreted as an M-array relation on the universe. I have explained it multiple times that when M is 0, then M to the 0 is a singleton.
Singleton.
So therefore, it will be interpreted as a subset of a singleton. So either that subset is the empty set or it is the singleton set. So this corresponds to it getting truth values, false or true. That's all.
Yeah, I got it.
Okay.
Okay, thank
you. Any other questions, Nitish?
Sir, so we defined our function f to the mn to m, where our n belongs to set of natural numbers, right?
Yeah.
So usually we can define our we can extend this natural number to a set of rational or set of R. Of course, it won't be our usual notation, but if we do this, how can we even make a language out of this? If we extend this definition to...
See, what is happening here, we are using n, to take the Cartesian product of n many copies of m. Now, if you just take n to be half, what do you really mean by square root of a set? Do you get my question? So this is the arity. So m to the half to m to the 3/4 to m. This doesn't have any meaning.
Okay.
Yeah, the arity function has to go to natural numbers. It has to choose some inputs. This arity is how many inputs it takes. You cannot say it takes half input, 3/4 input, 5/3 input.
Right, sir. Got it.
Yeah. Okay. Any other questions?
Sir,
Yes, Aditya.
can you explain what is interpretation?
Can you speak a bit louder? I can't hear you.
Yeah. Can you explain what is interpretation?
The interpretation of all these symbols is given here. Yeah, at here. So structure is also known as an interpretation for L, which means you interpret each symbol in your language. Each constant symbol is interpretation as an element. Each predicate symbol is interpreted as a relation, and a function symbol is interpreted as a function. So this is an interpretation for all the symbols in the language. Whereas if you need some interpretation for, let's say, terms, yeah, then that is the valuation. The interpretation of a term is a function. Yeah, so that is what we have done here. So interpretation is a general term associated to the semantic counterpart of the syntactic thing that we have defined. So the syntactic object could be a symbol in the language. Then the interpretation is defined in a particular way. It could be a term constructed out of those symbols. Then the interpretation is the value of that term. If your syntactic object is a formula with n free variables, then the interpretation is this, yeah, this double turnstile symbol. Like you say, satisfiability of a formula in a structure at a tuple. If your syntactic object is a sentence, then its interpretation is its truth value, whether it is true or false in a particular structure. So interpretations happen with respect to a structure, whereas syntactic objects just have their own standing. You don't need to choose any structure as such.
Yeah, it's okay.
Yeah, interpretations are relative to a structure. Yes, so one more, something similar to yesterday's tutorial session, that those who want to keep their videos on, they are welcome. Yeah, I like to see students' reactions. I learn a lot from that. Yeah, but of course, it's not mandatory. So any other questions?
Excuse me, sir.
Yes.
Sir, in the last tutorial session, in that question of finite colorable graph, sir, according to what we were taught in an introductory course on logic, like the set of all propositional variables is countably infinite, right? It is countably infinite.
That's your choice.
Okay, but so you mean to say even if we take uncountably infinite, completeness and compactness can be proven?
Yeah, even if your language is uncountable, you can still prove completeness and compactness.
Okay, so we were proven this in the context
so
of.
Yes, I mean, it is a good question. Like it doesn't just apply to propositional logic. It is also relevant in predicate logic or first order logic, that you only worry about, like, compactness is true because every formula is finite. Completeness is true because every proof is finite. And in any finite proof, you at most use finitely many symbols at a time. Yes. So that finiteness is what provides us with all these theorems. Yeah, you should not be worried about whether the language is finite or infinite.
Okay, sir.
Yeah.
Thanks, sir.
Sir?
Yes.
Yes, sir. So the proof for that, which we were talking about just now. So can we do this, that we can take that fragment of the first order logic or predicate logic, sorry, propositional first order language or propositional language, that fragment which contains only those many propositional variables that are present in the set that we need.
Yes.
The set. So we can do compactness by this way. So we will have
I mean, we don't we don't want to do it that way, because suppose there are some rules, and those rules could depend on formulas which already contain some other variables, but they are irrelevant. So whatever you said has to be proved.
Okay.
Yeah, it is not obvious that you ignore certain variables which do not occur there, and then you can still do it. So for example, what I'm trying to say, let's see. Yeah, so let's suppose this gamma that is on the screen, it is a set of formulas. Yeah, formulas of L. Now it contains free variables amongst x1, x2, xn, and each of the formula there maybe contains exactly one variable of them, whereas this theta doesn't contain any variable. But still you need to show that it is a logical consequence of gamma. Then you can't really throw out entirety of gamma.
Yes.
Yes?
Yes.
Yes. So, I mean, yeah, intuitively you will think that, okay, I will just throw out the variables which are not needed on the right hand side. But yeah, that cannot be done like that. So after taking some appropriate closures of these formulas and then taking the fragment which is required, then yeah, but it needs a proof.
Yes. Thanks.
Any other questions? Okay, in that case, we can proceed now. Yeah, so let us. Yeah, I mean, let me quickly remind you once again of what this logical consequence is, because that is important. So let L be a language, and from a set of formulas, you can say that a single formula is its logical consequence, which is written using this double turnstile symbol. If for all L structures M and all assignments A bar to X bar with A bar in M, whenever left hand side is true, then right hand side is true. Yeah, so once again, I want to emphasize that in propositional logic, we simply had to worry about for all valuations. But here, the problem is slightly more complicated, that for all L structures M and for all assignments A bar. Because you cannot define the truth of a formula in a structure without specifying the tuple at which you are evaluating the variables. Okay, any questions about this? Yeah, this is a very important notion. That
so can you repeat this?
Yes.
This one, maybe.
Yes, so we have to verify this condition that whenever phi is true in M at A bar, then theta is true in M at A bar for all L structures M and for all assignments A bar to X bar. So for all substitutions. So there are two quantifiers here. Yeah, there is a for all L structures and for all assignments. And the second one depends on the first one, because you first choose the structure M and then you choose the assignment A bar in M.
Sir, can you repeat what is assignment?
Yeah, assignment is just substitution. Yeah.
Okay.
So you see here that was done here in the definition of truth of a formula. So you say that this is a predicate symbol R and these are terms. So R T1, T2, Tm. Yeah, this is an MRE this is a formula. Yeah. This formula is true. You cannot say the formula is true. You have to say the formula is true in that structure at some assignments.
Right. Okay.
Yeah. So you can see like this example will help. So if the formula is just Rxy, then you have to assign some values. You cannot say that the formula Rxy is true in natural numbers. I mean, the question is, what are X and Y? So you have to answer that question by substituting, by assigning some values to X and Y. Like X is 5, Y is 6.
Sir, we could put any value as such, right?
Yes, but you have to verify the truth at any tuple.
Right.
Yeah. For all tuples, you have to verify the truth. Yeah. So this assignment is also equally important. Okay. So now comes the first definition of today's talk, that we say that if gamma is a subset of SL instead of FL, then we will say that gamma is a model of, M is a model of gamma. If if gamma is a logical, if each formula is in gamma is satisfied in M. Yeah, let me remind you again that SL is the set of sentences, which means there are no free variables in that formula. So for example, all these two formulas written here, yeah, for all W1 there exists W2 such that R W1 W2, and there exists W1, there exists W2, R W1 W2. These are two formulas which do not contain any free variables. So these are sentences. So for sentences, yeah, you can easily see, because there are no free variables to begin with, we get back what we did in propositional logic, that we just had to check that condition for all M. Yeah, for all L structures M, we had to verify if the left hand side is true, then right hand side is true. This assignment part just vanishes. So that's why sentences are interesting, and such collections of sentences is called a theory. Yeah, any subset of SL is called a theory, gamma. And we say that M is a model for that theory, gamma. Now, when you, in your syllabus, you have courses like group theory, ring theory. So you are actually referring to the axioms of groups. You are referring to the axioms of sets when you are talking about set theory. Okay, I hope you all understand what I'm saying. Group theory is the theory given by three statements. Those three statements, like for that particular language, the three statements are that the binary operation is associative, there is an identity element, or you can say that the constant symbol satisfies the identity properties, and for every element there is an inverse. So this is a collection of sentences, because there we say for all W1, for all W2, for all W3, W1 dot W2 dot W3 is equal to W1 dot W2 dot W3. Okay, I'm going to open a book. Yeah, so I can show you some examples of this. Yeah, I mean, this is for all. So this is group theory. So group theory, the word theory in that phrase, group theory, has a specific meaning. Yeah, these are the axioms. These are the sentences whose models are groups. Similarly, I want to give you one more example. Let me. I don't want to do this part. I just want to do piano arithmetic and I should have opened it before the lecture started, but I was busy with something else. First order theories. Yes. So yesterday you saw the theory of piano arithmetic. Yeah. Then the language of the theory of rings with identity. Yeah. These are the axioms on top of these axioms. So a ring is a model of the theory of rings. A field is a model of theory of fields. A linear order is the model of theory of linear orders. Then,
Sir,
yeah.
While talking about these things, while you're giving examples, can you just once again go back to the definition? I mean, I want to correlate.
Yes,
I mean, how it
sure.
was defined. That would help.
Okay, so by correlation, you mean like what is the meaning of a sentence, basically?
I mean, the definition, like model.
Definition of a theory. Yeah, okay.
Yeah, theory and model.
So gamma is a set of sentences. And we say that an L structure is a model of gamma if every sentence is true in there. So for example, if you take the group Z, Z plus 0, Z plus 0 minus, then the plus operation actually satisfies the axiom of being associative.
Okay.
Yeah, then this constant symbol 0, its interpretation, that is 0, 0 in integers, that satisfies the property of being the identity for plus.
Right. I mean,
Yeah, so that is what we are saying. So a model of a theory. Yeah, group theory. So every group is a model of the theory of groups. Every set is a model of the theory of sets. Then these are piano arithmetic axioms. And I just wanted to show you this Zermelo-Frankel set theory. Yeah, you are doing a course on set theory right now. Like set existence. There exists a set such that x is equal to x. Extensionality. So here, what is the language? The language of set theory consists of only one non-logical symbol, which is the belongs to. It is a binary relation symbol, binary predicate symbol. And equality is just from meta language. So you can see that all of these are formulas written in that language. Yeah, of course, I'm not going to explain this thing to you, but these are all axioms. Yeah, axiom of infinity, axiom of foundation, axiom of power set, axiom of union. So these axioms together, they define, I mean, they count as set theory. So a set is a model of theory of sets. If you change your axioms, then your names will change. This is Zermelo-Frankel set theory. You can have Neumann, von Neumann set theory, Gödel-Bernays set theory. Yeah, you change axioms, you will change something. Okay.
Okay, sir. Yeah.
Yeah. Now, yeah, to each theory, we can ask for the collection of its models. Yeah. There may or may not exist any model. Yeah. Then if there is no model for that theory, then you say it is unsatisfiable theory. But if there is a model, then you say it is satisfiable theory. Moreover, in the converse direction, if you are given an L structure M, then you can define its theory to be the collection of all those sentences which are true in M. Now, this truth is binary. And therefore, if theta belongs to SL, then if theta belongs to the theory of M, then negation theta will not belong to the theory of M. Yeah, both theta and negation theta cannot be true in a structure. And in fact, for every sentence theta, for every sentence theta, exactly one of theta or negation theta belongs to the theory of M. So this qualifies, actually this theory of M qualifies to be an ultra filter in the collection of all logical equivalence classes of formulas. And we are going to define what is logical equivalence. But yeah, I mean, just a minor comment that clearly M is a model of the theory of that structure M, but there could be many more models. I will talk a bit more about this tomorrow at the end of my lecture. Yes, Rupkatha?
Yeah, so can we say that like the names you mentioned, like the piano, I mean, whatever. The different parts of the set theory, different types of the set theory you mentioned just now. I mean, there were many names. So each of them are, each of them is a model of the thing called set theory, right?
Yes, model of the theory of, model of those axioms.
Yes. And that is referred to as set theory.
Yes, that is a set theory, correct.
Okay.
Any other questions about the notions of a model and the notion of a theory?
Yes, yesterday we are talking about universe. Can you correlate universe and model?
So universe is just for associated with a structure or a model. It is the underlying set of that.
So, universe is also in the symbolic part only.
No, universe is on the semantic side.
Yes, sorry, semantic part only. I mean, both of them are semantic part.
Yes.
Okay,
so
fine.
we have to first fix a universe. We have to fix interpretation of all the non-logical symbols in the language, which means constant symbol, relation symbol, function symbol. And once we have fixed that, that becomes an L structure. Yeah, universe is a non-empty set with all, and then an L structure is this universe together with all these symbols. And then given a collection of sentences, you can ask whether all those sentences are true in that structure. If yes, then you say it is a model for that theory. So a model is...
We start off with that universe, and then with that, recursively we get this model. Fine.
Yes. Correct. So this model is a specific structure with respect to a theory. Yeah, not necessarily that all L structures will be models of a theory. If you take the empty theory, yeah, if gamma is the empty subset of SL, then definitely all structures are models of that theory. Otherwise, you will like more number of axioms to satisfy, the smaller will your class of models be. And in the converse direction, we have that associated to every L structure, you can have the collection of sentences which are true in that structure. That is called the theory of that structure. And M just happens to be one of the models of that theory. Okay, so before I go ahead, I want to point out one particular formula that we discussed yesterday. Let me find it out. There exists... Sorry. I mean, okay, so let me say it out loud. So the formula which says that there exists a W such that X is equal to W dot W plus Y. You remember this formula?
Yes, it says X is greater than Y. Greater or
X
equal
is
to
bigger
Y.
equal Y. Okay.
Yeah.
Okay. So now I want to point your attention. Yes. The formula is here, 50. There exists a W such that X is equal to W dot W plus Y. Now, something specific about this, that this is a formula in the language of rings. The language of rings consists of a binary relation symbol for addition, binary relation symbol for multiplication, unary relation symbol for negation, and two constant symbols for 0 and 1. It doesn't have less equal in the language. But this particular formula, when interpreted, so its truth in real numbers is precisely the interpretation of the less equal symbol. Correct? So an interesting question is what happens when you ask for a similar formula in the language of rings over integers.
So can you, I couldn't get your question.
Yes. So what I am asking, can you find a formula phi 0 xy in the language of rings that when interpreted in the integers tells you precisely that x is bigger equal y? So that formula is true in integers if and only if x is bigger equal y. Are participants clear about this?
Sir, I think it should be something related to square root, because square root doesn't take negative values.
Correct. Correct. Squares.
Yeah, sure.
Okay. Yes. So squares is what we use in real numbers. Correct. So we can say that 3 is bigger equal 1 because there exists root 2, which witnesses the difference between them as square. Yeah, 3 minus 1 is equal to square of root 2. But how will you do the same thing in integers? Yeah, because root 2 is not an integer. So please think about this problem. Yeah.
I don't know. I'm just guessing. I like the Pythagoras' formula, x squared y squared equals z squared. If you put in, integers, it can give you back integers in some cases.
In some cases, but I want it to be true for all of them.
Okay.
Yeah, I want a formula phi 1, which so phi 1 is true in integers at a comma b if and only if a is bigger equal b. Okay,
so the bigger part is not in the language obviously, but it's coming from the interpretation, right?
Which bigger part?
X is bigger than y.
Oh yeah. No. That is just our understanding. Yeah, a
Yeah.
and b are two integers. I'm saying a is bigger equal b, but I
Fine.
want a formula in the language of rings. So only using addition and multiplication, which does that job. Such and many other such questions are quite interesting. So what this question asks you to do is to think about the expressive power of a language. What can that language say about a particular structure? Okay, so please think about this, and whenever someone gets a solution for this, yeah, let me know. Not necessarily now, I will wait until tomorrow. Okay, somebody says something in the chat. Okay. Yeah, there is a question from YouTube Live, which I will defer for now. I don't want to distract people. So what is the model for set theory, and give an example of a model for set theory? ZFC. Okay, so I'm not going to answer this question right now. I will defer it for discussion to tomorrow's tutorial session.
Okay, sure, sir.
Yeah. Thanks. Right. Yeah, I hope the participants got my question about integers. Right. I want to say something more while I'm on this topic, that the formulas which contain quantifiers, yeah, because we are at the topic of expressibility of a language. So what is expressive power of first order language? So look at this. So the quantifiers are interpreted as elements of the set, and this is clear from this T3. Yeah, there exists Wj is interpreted as there is some b in M such that M, so phi a bar b phi is true in M at A bar comma B. So I want to point out some constraints on the interpretation. Yeah, you cannot say that there exists a subset of your universe for which something happens. Okay, so our quantifiers only range over elements of the universe. They do not range over subsets of the universe. One example of an axiom, yeah, which uses quantification over subsets, quantifiers over subsets, is the famous completeness axiom for reals. Okay, completeness axiom. So it says, so Agniva, let me finish. Yeah, just a minute. So completeness axiom states that every non-empty subset of reals that is bounded above has a least upper bound. Okay, so just write it in logical terms and you will see that for every subset of real numbers, yeah, there is a quantification over subset that is bounded above. Like if it is bounded above, then there is a least upper bound. Now, this is not a first order formula. This is called a higher order formula. And if you study model theory, then you can actually show that there is no equivalent formula which does the job in first order logic. So this is a strictly second order formula. So our first order logic will try to capture a lot, and therefore my words here, yeah. So I said somewhere that yes, FOL provides a way to talk about algebraic structures. I mean, this least upper bound property doesn't come under algebra as such. Yeah, it is some higher order property. I mean, I know I'm saying these sentences, they could confuse some of you, but I still want to talk about why first order logic is not sufficient to do everything that we need in mathematics. There are some restrictions. There are some, there are certain things for which you need to consider some other higher languages. Now, Agnivo.
Yeah, so every ring is a group. So, so if we keep the plus operation like that, but we define the binary operation like x dot y is equal to y dot x if x not equal to y, and x dot x equal to x. Then then for any xy, x minus y is equal to x minus y dot x minus y, and that is the w that we want.
That is the w that you want.
Yeah,
no, that is still not true. Yeah, I mean, I'm simply so are you? I think you are talking about the integer problem.
Yeah, exactly.
Yeah, so in integers, like if you take 5 and 1 as your numbers, then of course 5 minus 1 is 4. Yeah, and for 4 you have what you need. It is 2 square, but not otherwise. And you cannot change. See, even if you change like you cannot change the meaning in integers.
Okay, fine. Because in the problem statement was only talking about the interpretation in terms of ordering, right? So, yeah. So
you cannot change the meaning of the symbols in integers. Just a moment.
Okay, fine. Then it's fine.
Yeah, so there are some, you have to work in the standard model of Z.
Fine.
What would be a concrete and simple instance of needing? I mean, least upper bound property of real numbers is a concrete and perhaps quite simple, because if you study calculus, you are definitely going to look at it. Yeah, that is second order logic. And from second order logic, there is no difference between second and third. Yeah, you are anyway quantifying over subsets. So and you have power sets. So Yeah, it doesn't matter what happens afterwards.
Hello, sir.
Yes.
Sir, in yesterday's example, you have given L group theory one example as for all W1, for all W2. W1 star W2 is equal to W2 star W1.
Yes.
Commutativity it is not necessary for a group. So can we include it in the L group sentence?
Yes. So the theory of groups does not ask for commutativity, whereas if you want to talk about the theory of abelian groups,
okay,
then you need that extra sentence. Yes, you add that sentence to your theory.
Okay. Thank you, sir.
No, yes. So Shashank, that's a good question. Yeah. So topology is not expressible in first order logic, especially the point set topology. Yeah, we need to talk about subsets and intersections of subsets and join of subsets. Whereas there is a first order version, but not necessarily finitary first order version. So that is the study of frames or locales, which can do that. Yeah. So where you forget about the space where you are taking the open sets, you just talk about open sets themselves, and it is some slight advanced version of lattices, and there you can do topology. It is called point free topology. Yes. Arul?
Yeah, I mean, like it's something similar to what you said right now, as in so the quantification, I mean, instead of doing the quantification over sets of predicates, I mean, or classes, we consider them themselves as predicates. So then you are sort of bringing it back to first order, right?
No, I'm not talking about making open sets as predicates. I'm just saying take the collection of open sets to be your universe.
Right. No, I mean, like, no, that is in this particular context. No, I'm just asking. So instead of, I mean, like, if the difference is in terms of where you are quantifying. So instead, if you, if the collections themselves are sort of considered as predicates themselves, so then the higher order is.
Then some problems could be solved, but again, like in topology, if you include each open set as one predicate, fine, but you still can't express the arbitrary union property.
Right.
Yeah. Okay. So those axioms will be indexed by the open sets themselves.
Right.
Yeah? Right. Okay. Yes, so there is another question from YouTube Live, and this I will just briefly answer. Is there a completeness theorem for second order logic, and what about any incompleteness theorem? So second order logic is very hard to study. There is no completeness, that is for sure. And incompleteness theorem, I'm not sure anybody has studied, because even first order logic is incomplete. So there is no hope of having second order logic as incomplete. Okay, so Ramakrishnan has given an answer to that question, but no, it's not correct. Yeah, continue thinking about it anyway. I will go ahead right now. Okay, so I will get back to this. So I wanted to say what is meaning of first order in first order logic. Yeah, first order means quantification over elements. Right. So now we are going to do some simple things, yeah, which we had done earlier for propositional logic. I will just state and then state the properties, define this logical equivalence of two formulas. So as usual, in semantic world, we don't want to continue talking about phi and phi disjunction phi as separate entities. We want to have some notion of logical equivalence. And as we did before, we say that two formulas are logically equivalent if for all structures M and for all assignments A bar to X bar, we have that the left hand side is true if and only if the right hand side is true at A bar. Okay, so this is our standard way of saying that. So Yes. So some simple standard logical equivalences I can show them to you here. Yeah, theta 1 x bar conjunction theta 2 x bar. Theta is logically equivalent to theta 2 conjunction theta 1. Double negation, elimination again. Then there exists wj. Yeah, so you can change the name of your variable, bound variable. There exists wj psi x bar wj is logically equivalent to there exists wk psi x bar wk. So you can swap the order of existential quantifiers. Yeah, provided the formula is totally inside both the scope of both of them. So there exists wj, there exists wk, there exists wk, there exists wj. And if a particular formula is free of that bound variable, then you can take the quantifier inside with respect to conjunction. Yeah, theta 1 doesn't contain wj, but psi does. So you can take there exists wj inside. Yeah, these are some of the standard logical equivalences, not all of them, but these are of course useful. Yeah. Okay. And like a simple proposition, and this says that you can take disjunctions on left hand side of the double turnstile symbol under some specific conditions. Let's not go into these details. You can prove this very easily. The most important property of this logical equivalence is once again that it is a congruence relation. Of course, it is an equivalence relation, but moreover, it also behaves well with respect to the connectives and quantifiers which we have. So if theta 1 is equivalent to theta 2 and phi 1 is equivalent to phi 2, then negation theta 1 and negation theta 2 are equivalent, and so are theta 1 conjunction phi 1 and theta 2 conjunction phi 2. This is not surprising. Now the only thing we need to add in the new one is that if psi 1 x bar y is logically equivalent to psi 2 x bar y, then replacing y by the bound variable wj and then putting there exists wj, the existential quantifier, those two formulas are also logically equivalent. So this is what we mean that it is compatible. This equivalence relation is compatible with our connectives and quantifiers. And just like we had the DNF there, yeah, some nice form for formulas, we have PNF here, pre-next normal form. So every formula is logically equivalent to a formula of this specific type, where we say that all the quantifiers are in the front and inside we have a quantifier free formula. Okay. So you can use these standard logical equivalences to take all those quantifiers outside. But of course, you shouldn't expect that all of them will be there exist. Yeah, so there could be there exist formulas and quantifiers, or for all quantifiers, universal quantifiers. Both of them are allowed in any order over here. Yeah, so any questions about this standard stuff? This is quite easy.
Sir, let's say we have some relation between WJ1 and WJ2.
Mm-hmm.
So
what is the meaning of relation between WJ?
Relation means, that, let's say plus or dot, those, what is it?
WJ1 as in the bound variable.
Yeah, I mean, inside psi x bar, comma, WJ1, comma,
Yeah.
I mean, in the pre-next normal form.
In the pre-next normal form, okay.
Yeah. So, how to relate WJ1 with WJ2? Let's say they, like, WJ1 and WJ2 are related with a plus symbol.
Okay.
Yeah. So how to put that? I mean, all of our those formulas, functions, etc. They are put outside this thing, right? Outside psi. They are put separately. Q1, WJ1, such things.
Mm-hmm.
So how to connect WJ1 to Wj2 using, let's say, Q1 Wj1, this formula, or what?
I don't understand your question, because what do you mean by relate?
Connect.
Connect in which sense? Like,
Okay.
these are variables. How do you connect variables?
I mean, the way we used to do, like, we would put
Can
a
you
symbol for.
Can you give me an example of what you want to say?
Okay. Like, let's say x1 plus x2, and we have in this psi of x bar, comma x1, comma x2.
No, what is meaning of psi of x bar, comma?
I mean, I'm not clear about x bar, but I think
X bar is a tuple of variables.
Okay.
So this is x1, x2, xn, and this is y1, y2, yk. That is a quantifier-free formula. So this is just the list of variables which appear in that formula, which could appear in that formula.
Yeah.
So variables have no connections between them. These are just symbols, independent symbols.
Yeah, I mean, I was talking about those symbols only.
Those symbols cannot have any connection between them. What you mean is that perhaps in a formula, you can have something like x1 is equal to y1.
Yeah, okay.
Yeah, so that could appear, but still I don't see what you want to say. Perhaps you should frame your question appropriately and then ask me.
Fine.
Okay. Yes. Any other question? Okay. So once again, I mean, logical equivalence classes of formulas, they will form a Boolean algebra. Yeah. So I'm repeating this even in the case of first order logic. It was true in the case of propositional logic. Here, the situation will be complicated. Yeah, definitely. We have got so much more to do with. Right. So now our main goal is to show the compactness theorem. So of course, we have said that a theory is satisfiable if and only if there is if there is a model for gamma. And we say that a theory is finitely satisfiable if each finite subtheory has a model. Okay, so let us look at this. Compactness theorem is the same statement, but you can only expect compactness theorem for a subset of the collection of sentences. Yeah, we don't expect anything for formulas, because sentences have truth values. Yeah, so we are just talking about whether that sentence is true or false. We did not define satisfiability for a collection of formulas. We just defined satisfiability for a collection of sentences. Yeah, so please keep that in mind. So we are talking about a theory being satisfiable if and only if it being finitely satisfiable. Okay, so we shall prove this theorem by constructing an average structure of a family of L structures. Yeah, so this is something very new for most of you, I think. Like, we are going to take an average. Yeah, this, and the word "an" is important here. Yeah, there could be several different averages of a given family of L structures. Okay, there could be multiple averages, and those averages will depend on ultra products. And ultra products are indexed, I mean, they correspond to an ultra filter. So before I go any further, so I just want to check how many people are actually listening. So the question is, so I will take a poll. Have you studied ring theory before? Just a random question. Ring theory or group theory, let's say. Have you seen group theory before? Yeah, I have given you the poll. Please vote. Okay, so still people are answering. Okay, so after 20 seconds, I can only see half of the answers. So the rest half are away from their computers. Yeah, so 93% of you have said ring theory, group theory, I think that you have seen. Only 2% haven't seen them. Yeah, it doesn't matter so much. What I'm going to say is that if you take real numbers and you take the product of real numbers with itself, real cross reals, then does this algebraic structure have the structure of a ring? Yes, can anybody answer whether R cross R has the structure of a ring? Yes. What are the operations?
Pointwise addition.
Correct. Pointwise addition, pointwise multiplication. Then order, if you want to define, then what is the order in this? Deepanvita?
Yes, sir. Like say x1, y1, and x2, y2 are in say R cross R, then we say that we can define an order like x1 is less than x2 and y1 is less than y2.
Yes. Yeah. Dictionary order is one of the possibilities, but we don't want to do that. We just want to do it pointwise. Yeah. Dictionary order actually needs some ordering on the index set itself.
Yes, it does.
And we might be dealing with infinite products, and that is just a set, not necessarily an ordered set. So that's why we don't want to deal with dictionary order. It is just the pointwise order. Then 0 will be 0, 0, and 1 will be 1, 1. Okay.
Okay.
Now, one more question. Like, is it a field? Like, are there any zero divisors in R cross R?
Yes.
Yes, Ujjwal, what are those?
1001.
Why? Okay, 1001. Yes. So this is not a field. It is a ring, but it is not a field. Nitish, there are zero divisors. Yeah, 1001. If you take their product pointwise, then
there are zero devices. Any 30 or 03 like that.
Yes.
Got it, sir. Got it.
Yeah. Okay. Yeah. So there are zero divisors in R cross R. Yes.
Sir, what is a zero divisor?
So two non-zero elements multiplying to give zero. That is a zero divisor. So any of them, a non-zero element which when multiplied by some other non-zero element gives zero.
Okay.
Rupkatha, are you a master's student?
Sir, I'm a second year student.
Second year undergraduate?
Yes, sir.
Okay, fine. Okay, so yeah, so A comma 0 and 0 comma B are zero divisors in general. So there are zero divisors. So R cross R is not a field, but somehow we would like to make it into a field. Yes. And not just that, not just R cross R, I would also like to define some field structure on, let's say, R cross R cross R cross R taken natural number many times. Okay, so let's say sequences of natural numbers. And of course, I mean, sequences of natural numbers also with pointwise ordering, then it is not a field. It will still be a ring, but not a field. Okay, now I will take a diversion from the main lecture, and I will tell you a story at this point. Yeah, this story is from 18th century. So when Newton and Leibniz were still fighting about getting credit for calculus, developing calculus. And do you know what was the original definition of continuity? Anyone who knows a little bit about that history of calculus?
Sir, I think, I mean, there was I mean, person from church who, worried about this limit. So, how does the limit tend to 0? So, after that, the sequence was constructed. That's what I know.
Okay. Yeah, I mean, you are close, but not exactly there. Anybody else?
Is it this definition? I mean, the standard school level definition that we're given, as in you can draw the curve with a.
Okay, drawing is the geometric intuition, but what they said actually, that if 2 points in the domain are arbitrarily close, then their images under that function in the codomain are also arbitrarily close.
Infinitesimal.
Infinitesimally, exactly. I was waiting for this word from the audience. Yeah, so thanks, Dhruv. So they wanted to say that if 2 points in the domain are infinitesimally close, then those 2 points are their images are also infinitesimally close. That is meaning of continuity. But what is the meaning of infinitesimal? An infinitesimal is a number which is positive and which is smaller than all positive real numbers. That is the intuition they had. At that time, mathematics was not rigorous. Okay, so something which is positive but smaller than every 1 by n, let's say. Now we know that such numbers do not exist in real numbers. Yeah, if something is smaller than each 1 by n, where n varies over natural numbers, then of course it has to be non-positive.
Yeah.
But non-positive is not allowed because you are also putting one extra condition on top of that. That it has to be positive. So infinitesimal was a beast that was used to define something very important, but later on people realized it doesn't exist. Then what to do? And then around the turn of the 20th century, people realized that there is an alternative, and that is why they invented this more complicated definition of epsilons and deltas, which we study in our syllabus. Yeah, for all epsilon greater than 0, there exists delta greater than 0. But nonetheless, this idea lingered with mathematicians. And after 200 years, yeah, so this earlier development was in early 18th century, but Abraham Robinson, after 1950s, he actually found the meaning to the word infinitesimal. Abraham Robinson is a model theorist. Model theory is study of first order logic from semantic perspective, where compactness theorem is just the beginning. So lots of questions that you are asking, yeah, model theory will be like application of first order logic to mathematics. So if you are more interested in learning logic from mathematics perspective, you should study model theory. Right. So Abraham Robinson actually gave a formal definition of an infinitesimal. And if you want to add, so infinitesimals, of course, do not exist in reals. But you can add, like forcefully add an infinitesimal there in such a way that the resulting structure becomes a field again, an ordered field, just like real numbers. And in fact, he showed that the resulting structure by adding infinitesimals and of course their multiplicative inverses, which are known as infinities. Yeah, infinitesimal is very small but positive, and infinities are their multiplicative inverses, which are very large, like bigger than every natural number. So these infinities and infinitesimals can be dealt with in a purely algebraic manner in such a way that this resulting structure is also a field. It also has an order It also has addition, multiplication, and everything that you would need. Yes, Siddharth Koduri, can you speak? Yeah, rather than writing. Okay, serial number system. Yes, okay, fine. I'm not going to go to serial numbers. I'm going to hyperreals. Okay, fine. I'm going to hyperreals. So hyperreals is a model. Yeah, it is a model of non-standard analysis. Yeah, so that's what I'm going to do the next, where you can talk about these infinitesimals and infinities. You have just added more numbers to reals, and those are known as hyperreals. Yes. So let us look at the construction of this, and then if you have any questions, of course, feel free to stop me at any point. So let Rn denote the set of sequences of reals indexed by natural numbers. Yeah, like A1, A2, An, ... infinite sequences. Under pointwise addition and multiplication together with zeros and ones, Rn has a ring structure. We already saw that. Now we have to put some equivalence relation on this Rn so that the equivalence classes behave like hyperreals. So they have some algebraic structure and order structure, which is an extension of the standard real structures. Yes, ordered field of reals. Okay. Moreover, you can also pointwise compare sequences to make it into an ordered ring, but not an ordered field like real numbers. I have just written all these things down. And here enters the notion of ultra filters and filters. So, okay, you have already seen this. So let F denote the Fréchet filter on M, which means the cofinite filter. All those subsets of natural numbers which consist of cofinite subsets. So you can easily verify that this Fréchet filter is actually a filter. Okay. Now our idea is that, so especially about this ordering. So we want to say that the sequence A1, A2, An is less equal B1, B2, Bn if An is less equal Bn on a large subset of natural numbers for a large set of indices. Yeah, we don't want to say that it has to happen at every coordinate. We want to say that it happens on a large set of indices, whatever large means. And we have to define what large means. We have to find out the properties of large subsets of indices, which means subsets of natural numbers. And the formal, like if you try to put some conditions, like suppose, let's say even numbers. Yeah, even numbers is a large subset. Then, of course, even numbers plus a single one. Yeah, that should also be a large subset. So anything which contains a large subset should be a large subset. Then like, of course, we don't want to declare any finite set to be large, but then the cofinite set should be large. Yeah, because that is what our intuition tells us, that you have only left finitely many elements. So yes, of course it is large. Of course, the entire subset has to be large. Right? And you put some more restrictions and you eventually recover the definition of an ultra filter. And because of our intuition that we don't want finite subsets to be large, we have already started with the Fréchet filter. And U is any necessarily non-principal or free ultra filter containing F. So what I'm trying to say, that use axiom of choice or the Boolean prime ideal theorem, Boolean prime filter theorem to construct, construction is a wrong word here, to obtain an ultrafilter which contains F. Okay, so it is actually a property you can check. So I was just looking up the internet this morning, and I found, yeah, there is a statement which states math stat exchange. There is a question which will show you, and you can also check that any filter, any ultrafilter containing F is necessarily free, and any free ultrafilter will necessarily contain this pressure filter. Okay, so it works both ways. Yes, Satvik. Are you there?
Sir?
Yes, yeah.
So this non-principal, so the free, so you have a filter and you consider, you fix a point, and then you consider all the subsets containing that fixed point.
Yeah.
So this is how one would usually construct.
So
I mean,
those ultrafilters are known as the principal ultrafilters. Yes.
Okay.
Yeah.
Yeah.
And what I'm saying, that any extension of F is necessarily a non-principal or a free ultrafilter.
Okay. Thanks.
Yeah, and you definitely need axiom of choice or some weaker version of it to guarantee its existence. So what is meaning of large? Yeah, the large thing that I was talking about. Large means that it has to be an element, that subset of natural numbers has to be an element of that ultrafilter. Now, because you know the property of ultrafilters that either a subset or its complement belongs, so there are some unintuitive things happening there, that if the subset of all even natural numbers is large, then the set of all odd natural numbers is small. Yeah, so these are just some, this is the price we have to pay for using ultrafilter, but there is no option. So now we can define an equivalence relation on these sequences, saying that two sequences are equivalent if and only if the set on which they agree is a large set. The index set on which they agree is a large set. So this is the equivalence relation. And now things become magical immediately. Yeah, so you consider star R, the hyperreals, to be the collection of equivalence classes of sequences of real numbers, modulo this equivalence relation, and you can verify that it is lengthy. Yeah, you can verify that star R is also a ring with respect to induced operations. You have to use all the properties of filters. Yeah, and moreover, it also has order. This order is again defined in a similar manner like this equivalence relation, that the sequence, the class of the sequence an is less equal class of bn if the indices on which an is less equal bn is a large subset of natural numbers. Yes, Ramakrishnan.
So this large thing, it has some faint resemblance to this almost everywhere property in measure theory. Is it?
But okay, so in measure theory, the complement of here the distinguishing characteristic of ultrafilters is that either a subset or its complement is always there, is in the ultrafilter. Yeah, so that will not be satisfied with the almost everywhere property there. Yeah, so our idea is that the class of an is less equal class of bn if that less equal relationship is true on a large subset of indices. Now this depends on your choice of u. Yeah, So this star are a model of hyperreals that depends on your choice of view. So that's why I said it is an average. Yeah, so I should say that. So this star R is an average of natural number many copies of real numbers. Okay, that is how we have to view it, as an average structure. And what is more important is that it is in fact an ordered field. So what was missing? The field property, the defining property. So I just want you to take a minute to think about this. So what will happen? So you want to say that in a particular representative of this equivalence class, you choose a non-zero element, which means the set of indices where those coordinates are 0 in that sequence is a small set. Similarly, you choose another sequence where the set of coordinates, the set of indices where the entries are 0 is a small set. Then by using ultra filter properties, you can show that the product of such two non-zero sequences, is again non-zero. So when is a sequence 0? If it contains 0 in a large set of indices. So if it is non-zero, then it can contain 0 in a small set of indices. And you have to use ultra filter properties to show that there are no 0 divisors in this star R. Okay, any questions so far?
So we embed reals by the constant sequences only?
Yes, we embed reals by the constant sequences. Correct.
Okay.
And what are infinitesimals here?
Yeah. So the sequence is converging to infinity?
No, the sequence is converging to 0, like 1, 1 by 2,
Oh,
1 by 3, 1 by
I mean,
4.
infinities would be that.
Yes. Okay. So 1, 1 by 2, 1 by 3, 1 by 4, that is one infinitesimal. And with respect to this ordering, you can actually check that it is less equal the constant 1 by n sequence for each n. Yeah, because that constant 1 by n sequence up to a certain point, up to nth entry, this an will have bigger entry, like an will be bigger than bn up to some n naught. But after that, all the entries of ans will be smaller than the corresponding entries in the constant sequence. And because of the Frechet filter condition that we have chosen a free filter containing the Frechet filter, so we have only removed finitely many coordinates. So of course, this less equal relationship is satisfied with this definition.
So sequences converging to some C would be infinitely close to that real number, right?
Sequences converging to some
real number alpha, say.
Some real number alpha, yes.
Will be infinitely closer to
correct,
that.
Correct.
What will happen to oscillating sequences?
They will just be there. So so you can define the notion of a finite hyperreal, and there is a decomposition of every finite hyperreal. That every finite hyperreal can be written as its standard part, which is a real number plus an infinitesimal. Yeah, so there is an entire theory. This field of mathematics is called non-standard analysis. And yeah, I mean, as I described, so there are some infinitesimals here, and there are infinities like the sequence 1, 2, 3, ... That sequence, the equivalence class of this sequence, that is infinity.
Yeah.
And that will play the role of multiplicative inverse of 1, half, 1 by 3, etc.
Yeah.
So that their product is 1. constant one everywhere. Yeah, so there are many beautiful properties here. So a hyperreal number could be finite or infinite. It could be infinitesimal. Infinitesimals are close to zero. Yes, there are many questions I can see.
Sir, okay, yeah.
Okay, I will give you chance one by one. So Nikesh first.
Sir, you said that any sequence converging to 0, that means can we take like -1 by n or the negatives also converge?
Yes. So you have an ordered field. Yeah, so negative numbers will be less than 0.
No, but you said that the infinitesimal is positive, right? So
no, infinitesimal, but like you can also have negations of infinitesimals. Like
no, I'm saying if you take -1 by n, then it will converge to 0.
Yes, so that is negation of an infinitesimal. If epsilon is an infinitesimal, then minus epsilon is also an infinitesimal. I mean, I was just trying to motivate that by saying that, okay, is there anything after 0 and below 1 by n for all n? That's why I said positive. But yeah, of course, there could be negative infinitesimals.
Okay, understood.
Yeah. Aditya.
Sir, so Professor B.V. Rao defined limits for bounded sequences. So if you have a bounded sequence, and
yeah, I don't think I looked at that example carefully. I haven't seen that. So perhaps, yeah, I will have a look at that and then I can perhaps try to answer your question. Yes, Dhruv, you had one more question.
Yes, sir. So can you give an idea of what happens to this sequence -1 power n into n? So it is even terms are going to infinity and odd are going to minus infinity.
That is just a sequence and
well, I mean, where will it lie in this order?
So depending on whether even numbers form a large subset or not. Yeah, if even numbers form a large subset, then actually that is in the same equivalence class as constant one. On the other hand, if odd numbers form a large subset of indices, then that will be constant -1 sequence.
So there is also some inherent checking of well-definedness we need to do.
Yes. So there, like a single sequence is not an element. Its equivalence class is an element.
Okay. Interesting.
Yeah, so this is really interesting. Like you can study it further yourself. But okay, let us go a bit further. I want to finish my lecture within next 7 to 8 minutes. So now I don't want to talk only about real numbers. So here I took natural number many copies of real numbers, but here is some theory. So here I define the product of an indexed family of L structures. So I'm starting with an arbitrary language L, first order language L, and a first order structure M. Yeah, Mi is an I index family where I is a set, and the product structure is just defined by pointwise operations, pointwise function symbols. Constant symbol is just the tuple consisting of its interpretations, and M-array relation symbols are also interpreted pointwise. So please go through that yourself. The only thing that I want to highlight here is that the universe, the product of MIs consists of choice functions, which you have seen in the first lecture. So it is the choice function from set I to union of MIs such that Fi belong to Mi. So here we are, of course, assuming axiom of choice to have existence of choice functions. So the choice functions are the elements of your universe of the product. Okay, so the rest of the things, although tedious to write down, they are quite standard. Everything just happens pointwise. Okay, so I don't want to go there. And you have already studied ultra filters, so I won't say anything about that either. Yes.
So one thing, I mean, what is this point-wise? I mean,
Point-wise means each component. Okay. So like I is the index set. So for all little I, you have to check that. So if you want to define addition of AIBI, comma, let's see, sorry, AIAJ with BIBJ, then you will do AI plus BI and AJ plus BJ. Yeah, so that is point-wise.
What would be it otherwise? Let's say if it were not point-wise.
I don't know. I don't know. Without knowing anything extra, it has to be point-wise here. If you know something more about the structure, then you can perhaps define some different operations, but this is the natural way, as you say. Yeah, what it can't be anything else. Okay, so you define a relation on this product with respect to an ultra filter by saying two elements in two choice functions, yeah, or two sequences indexed by I, however you want to look at it, are equivalent if and only if the set of indices on which they agree is large. Again, you take the quotient of this product structure by this equivalence relation, and you define and you call it the ultra product with respect to these interpretations. Like the constant symbol in the ultra product is interpreted as, you take CMI, like its interpretation in the product structure, and you take its equivalence class, and so on. Like these are tedious thing to just write down, and you might get intimidated by these fancy notations, and you have to also check some well-definedness somewhere. But these can all be done. They are straightforward verifications. If you have patience, you can go through them. So that's why I did not say anything about the general structure. I just said hyperreals are interesting, and this is a generalization of the construction of hyperreals. The main point is that the ultra product that we obtain here, yeah, the product quotiented out by the equivalence relation with respect to an ultra filter, that is an average, yeah, that behaves like an average of that structures. And what do I mean by that? So I will just state this theorem and I will take questions. So suppose L is any language, MI is an infinite family. I mean, infinite is not really necessary here. Is a family of L structures indexed by a set I. So capital I is a set, that is important. And phi is a formula. Now, A1, A2, AN are elements of the product structure, which means they are choice functions or tuples, however you want to understand them. And U is an ultra filter on I. Then the ultra product, yeah, the ultra products, so phi, this formula phi is true in the ultra product at the equivalence classes of A1, A2, AN, if and only if the set of all indices where phi satisfies phi is true in the ith structure Mi at the corresponding coordinates is a large set, which means belongs to U. Okay, so just have a look here. Yeah, if and only if n belongs to n, such that an is equal to bn is a large set. So we are just generalizing this. Yeah, so an is equal to bn is a formula. Yeah, x is equal to y, that is a formula, and that is being satisfied at a bar comma b bar, like the sequence a and b. So we are just generalizing this to an arbitrary formula. Yeah, so phi is true in Mi at appropriate coordinates, and the collection of all such indices is a large subset. So this is an if and only if statement, because U is an ultra filter. And because of this, okay, so this could be a bit intimidating in the first go, but remove dependence on these elements. Yeah, so let us say phi is our sentence of L. Then phi is true in the ultra product if and only if phi is satisfied by a large number of component structures mi, m sub I, small I. Now, in particular, when all the mi's are isomorphic to R, yeah, you can see that any so any large subset is non-empty. So you can show it, yeah, with very little effort, that phi is true in mi if and only phi is true in R. And that is why every first order sentence which is true in R is also true in its ultra power. Yeah, which means in hyperreals. So first order statement is true in reals if and only if it is true in hyperreals. So this is what Walsh's theorem gives us. Yeah, even though it looks like L, it is Polish letter W, Polish letter, so we pronounce it as V, and this is Sh. So Walsh's theorem. Yes. Somebody wants to say something? Okay.
Amit, I have a. Can you hear me, Amit?
Yes, I can.
No, I don't have a question on your lecture, but I saw that you shared my book.
Yeah.
Now it will be very convenient for me also to share my book. So can you show me the technology sometime?
Yeah, sure. Just give me a call when the school is over. Yeah.
No, not school is over.
I mean today's school.
You mean today things are over?
Yes.
Because it will be nice for me to also share my book. Huh?
Yes, sure.
Because there are things which are quite cumbersome. I have not written.
Yeah.
But if I display that and kind of give them the idea how to go.
Yeah,
so
give me a call.
Actually, that is very vital for me. Huh?
Okay, sure.
Okay. Yeah. So this shows I was also listening, but not continuously. In the meantime, I took a bath and.
I mean, who am I to teach you?
No, don't worry. Everybody learns from everyone. Huh? Okay. You see, now I am going to fight with Bibi Rao. Huh? Though he is my teacher and very respected teacher, I am very grateful to him. No. Everybody is a teacher of everybody, and everybody is a student of everybody. No, that is my attitude.
Okay. Yeah, any questions about my what I said? Like these things are hard to understand in the first go, but please read them carefully. Nikesh?
Sir, you told that while combining the hyperreals, the real number becomes a field. How does it become a field?
Because there is a formula which states that there exists a y. So whenever x is non-zero, yeah, let me try to show it from SMS's book. Yeah, it's already there, and I don't need to do more efforts. Yes, please look at this formula 10. Yeah, for all x, if x is non-zero, then there exists a y such that x dot y is equal to 1 and y dot x is equal to 1. So it says that for every non-zero number, there exists a multiplicative inverse.
Okay.
Yeah, this is a sentence of our language. And what I just showed, that a sentence that is true in real numbers is also true in any of the ultra product. And because hyperreals are an ultra product, this sentence is true in there. That is the beauty of Walsh's theorem and the strength.
Okay. So while you mean hyperreals, then what is the term used to denote only the infinitesimals?
Sorry?
What is the term used to denote only the set of infinitesimals, or is it only
there is
one?
There is lot of notation. Nikesh, you can check the Wikipedia page itself. Yeah, it will tell you a lot.
Okay, sir. Okay.
Yeah. So Shashank.
Yes, sir. So what we got was from the Walsh theorem that any first order formula that is true on reals is true on hyperreals.
True in.
Sorry, true in hyperreals.
Yeah.
So that means that any property of real numbers which is expressible in first order language is also like the hyperreals also follow that property.
Yes.
Any first order property.
Any first order property that is true in
Just
reals.
not
Yeah.
Restricted to being an ordered field or something.
In model theory, it is called an elementary extension. Okay. So yeah, because you asked this question, I will go back a little bit. So look here, I said that if you take the theory of M, which means all the first order sentences which are true in M, then M is one of the models. So just now we gave an example of a model of theory of real numbers, which is not real numbers.
Yes.
Okay, so star R is also a model of the theory of real numbers.
And so does it also have some extra, is the theory of hyperreals bigger than the theory of reals? So we have some extra
it has to be. It has to be. See, any theory of structure, I will talk about it tomorrow a bit more. Yeah, what is meaning of a complete theory? So this theory is already complete. You cannot add anything extra. If you add something, some other sentence which is outside, then it becomes unsatisfiable.
Okay, so it's a maximal set in.
It is a yes. Complete theory is a maximally satisfiable theory. Yes, maximal satisfiable theory. Yes. So you cannot have anything extra. The first order sentences which are true in reals are precisely the sentences which are true in hyperreals. It goes both ways. It is if and only if. Yes, Prasenjit. Prasenjit,
Sir,
yeah.
So in the completeness theorem, proof of the completeness in propositional logic, you extend a consistent set to a maximally consistent set, which is a ultra filter. Yeah.
Which is an ultra filter, correct?
Again, in the first order logic, when you define a theory corresponding to a model, you say that this is an also ultra filter because either a formula is true or a sentence is true or its negation is true.
Yes.
Yeah. So my question is that in first order logic for a ultra filter, we can always define a L structure which model that ultra filters.
Yes, you can.
Okay. Or one of the question is why we define satisfaction for only for the set of sentences, not arbitrary formulas.
No, we have defined satisfaction for formulas, but you need some extra data. That you need the assignment to variables. See that we have defined that, like that is meaning of satisfaction. Satisfaction is this double turnstile symbol. So we say that theta is true in M at A bar. Now there is no necessity of A bar while dealing with sentences. That's all.
Okay.
Yeah, so you can define satisfaction for formulas as well. A formula is true in a structure if at a particular tuple.
Particular coordinate or tuple.
Yeah, tuple, yeah.
Or also one more question is that you say that completeness theorem is not hold in first order logic.
Completeness theorem is not true. No, completeness theorem is true in first order logic.
I thought.
No, so I said yesterday that I don't want to go into the proof theory details. So I just showed you the deduction system, deduction calculus for first order logic at the end of my talk. And I said there is completeness theorem, but I'm not going to prove it. Because I already did something for, this school is not sufficiently long to prove that. There is, first order logic, predicate logic is complete.
Okay.
Yes. So Shashank, do you have?
Oh, no, sir. Sorry, sir. That was from
Amit.
Okay. Yes.
Amit, will it be possible for you to share during my lecture my book today? Or is it very difficult?
No, it is possible. Yeah.
Okay, at one point will you be present in my lecture today?
I will try to be. I have some work to do, but I will, yeah, my computer is usually on.
Okay. Because at one point it may be, is Sujata there? Sujata?
Yes, I'm here.
তুমি কি পারবে? Will you be able to do?
SMS, can I take the questions first? Yeah, so that I mean we
okay.
can talk in private. Yeah?
Okay.
Nikesh, you have a question?
Yes, sir. While you are mentioning about the complete theory, does it make sense that complex numbers form the complete theory for real or hyperreals? You told about the elementary extension, right?
Okay, you are confused actually. So complex numbers do not have any order.
Yes.
Yes, so complex numbers and real numbers have no connection as far as elementary equivalence goes. Yeah, that is one simple thing. Then you can also, so if you have any one variable formula, yeah, P of X, then there exists W, P of W is equal to 0. That is true in complex numbers. That is the fundamental theorem of algebra.
Yes.
Whereas this sentence is not true in real numbers. Yeah, for example, x square plus 1 is your formula. It is not true in real numbers. So complex
but everything will be satisfiable in complex numbers, right? Everything will be true, like most of the things.
What do you mean by everything? You have to talk about formulas. Not every formula is true in any structure. Yeah, because you can only satisfy either a sentence or its negation.
Okay.
You are confused about a lot of things. Just go through it sequentially. Yes, so there is one question in my chat. Yeah. So Ramakrishnan says that he's not clear about why we started studying hyperreals out of the blue. Yeah, I mean, very valid question. I wanted to talk about Walsh's theorem. And for Walsh's theorem, you need to talk about ultra products. But to give the definition of ultra products is dry. Yeah, I mean, I will just say that this is the interpretation, you do it this way, this way, this way. But that you are not going to, I mean, you are not going to gain by doing that. So therefore, just like I introduced terms and formulas, using the example of polynomials, polynomial identities, and so on. So you can, I wanted to give you an example of a construction of ultra products. And therefore, I talked about hyperreals. Yeah, this is a commonly studied construction of ultra products in mathematics. Are you there, Ramakrishnan, in the audience?
Yes, I'm here.
So, yeah, you understood what I said? Yeah, I wanted to motivate the construction via an example, which itself is interesting.
Okay, yeah, okay. I was lost. I mean, amidst the previous discussion, where did this suddenly creep in? Yeah, just that. Okay.
Yes, true. Yes. Any other questions?
Excuse me,
Aditya?
sir.
Yeah.
Can I go on, sir?
Yeah, sure. Aditya or Ujjwal, who is speaking?
This is Ujjwal, sir.
Okay, Ujjwal.
Aditya is not speaking.
Yeah, Ujjwal, you can say.
So, I think I'm not sure about this thing. I think I've been able to show somehow that the hyperreals actually don't have the least upper bound property. So I just wanted to verify, is that
okay?
Correct.
Okay, I mean, let us defer that discussion to private one. Yeah, no, not we are already confusing people. Yeah.
Okay.
You can send me an email and we can talk.
Okay, sir. Yeah. I just wanted to verify if there is any chance of the hyperreals being isomorphic to R. That's not there, right, sir?
No, of course not isomorphic. Yeah, you have many more hyperreals, like just their cardinalities are different. So forget about an isomorphism.
Oh, right. Okay.
Yeah.
Yes.
Yes, the organizers want me to stop now. Aditya, if you have any quick question or...
It was related to that question only. So completeness axiom is like second order property.
Okay.
Yeah.
I mean, we can defer this discussion to tomorrow's tutorial session. And Dhruv?
So can you check the answer I sent you in the chat?
Yes, wait. No, that is not true yet. You take different examples and that won't work.
Okay, sir. Okay, I will check.
Yeah, please.
I have a doubt about the problem you asked in that ring theory thing.
Yeah.
So there you by x greater than equal to y means that so if you have a evaluation map say s, so that the sx is greater than equal to sy, right? I mean, by meaning that you mean that only, right? So if x y that are in the language, so is there any evaluation s so that sx is less than equal to sy for all s?
What is meaning of s?
S is the evaluation map. It gives meaning to the terms of the.
No, I don't think I'm getting your question.
So like x equals to w dot w plus y. So if suppose it holds, so we want so it should imply that x greater than equal to y means that so the x greater than equal to y is not defined, right, as a term. So so rather its evaluation should be ordered, right? That's what I'm.
It's evaluation. Yes. So it holds true at a comma b if and only if a is bigger equal b.
Yeah, here a is bigger equal to b means the evaluation of a and evaluation of
evaluation. No, I'm not talking about evaluation. I'm saying assignment to those variables.
Yeah. Okay. Assignment. Yeah. Fine.
Yeah.
So
assignment is different than evaluation.
So here in the solution we have to somehow find that assignment, right?
No. Assignment, for any assignment, that should be an if and only if statement. You have to find a formula phi which is true in Z at a comma b if and only if a is bigger equal b.
So the formula you have already given, right? X equal to w dot w plus y.
Yeah.
It's a ring structure we have to find, right?
No. Ring structure for Z is known.
Okay.
You have to find a formula. I haven't given you the formula. That formula works only in real numbers, not in integers.
Oh, okay. So I can really repeat the problem, again.
Yeah. She's here back. Yeah, I have saved the chat for those who have written their questions in the chat. Yeah, I will answer them tomorrow. Yeah, whenever I have, like, it's my time again.
So there are a few questions in the YouTube as well. So maybe you can address them tomorrow. Now that it's time. Yeah. So thank you so much, sir. Now we'll break for 45 minutes and come back at
sorry. There is one more thing. Yeah, Sujata wants to announce something.
Amit, it's
Yes.
already 15 minutes late, so I don't want to.
Fine.
Have lunch. Let everybody have lunch and come back. We will
fine.
Later.
Okay, we'll talk to later.
Okay, sure. Okay, then we'll meet at 2:15 for the next.
Fine.
Yeah, sure.
Okay.
Thank you.